21 billion euro, and that's the major challenge, how to make this whole project cost effective. So what I mean that, so also as the new advances are concerned, the CERN has contributed a lot, and the discovery of the the first antiparticle, the positron, which is utilized in this super collider. Also, the discovery of the positron is also very important in the sense that this is the first antimatter, and of course we do not have antimatter in this universe, but the creation of the antimatter, it can be very much useful in the various technological advancement. It can be used for propelling rockets also if we have enough antimatter. So the antimatter searches are also, they will be utilized in this CERN project also. So not only for electrons, but for example for the protons also, and for other particles. So they are certain new advancement and proposed advancement, and I quote, this is a long way to go, and I quote Einstein, because there will be many hurdles in coping with the situation, especially in this situation of the corona pandemic. But I quote the Einsteins that for the younger people, for the younger scientists, the younger teachers, that no matter what field you enjoy, you should stick with your desire. Think differently. And that's what everything, then everything goes properly, right? So the invention of the new things, for example, here for the benefit of the society, it goes like this, and Einstein also used the same procedure. If you see his life history, so think differently and enjoy whatever you do. Stick to your new desire, and so I would like to. I'm sure that the deliberations in this conference by various invited speakers, scientists, and researchers shall prove instrumental in generating great deal of the knowledge and a source of the inspirations to the younger researchers and in the various branches of the physics. And it will fulfill the motto of this conference, a promise to the society. The various topics covered in this conference will definitely prove to be a triggering agent to the various to further motivate the young people in colleges and the university. And I salute to the organizer that in the colleges where we have lots of problems, we do not have proper infrastructure, we do not have the geographical conditions are very difficult. Even then they are organizing this conference, inviting the new ideas and discussing these new ideas in the field of the physics. So I congratulate all of them. I wish all the best for the grand success of this e-conference, and I inaugurate the conference for the benefit of the society. Thank you very much.
Thank you, Professor Chandolaji, for your thoughtful address. It is now my pleasure to introduce you to our chief guest, Professor Sachin Maheshwari. Professor Sachin has done his PhD from Mechanical Engineering Department, IIT Delhi. He is working on an arc welding, hardening of steel, matrix composite, and published several research papers in this field in national and international journals. Currently, he is professor and head of Department of Manufacturing Process and Automation Engineering at Netaji Subhas Institute of Technology, New Delhi, and also as a Dean of Industrial Research and Development. Now I will invite Professor Sachin ji. Sir. Sachin sir. I think Sachin sir has left.
Good morning to all of you. Am I audible?
Yes, sir.
Yes.
Thank you, friends, for inviting me to a physics conference. It's little unusual to be invited in a physics conference, a mechanical engineer being invited to physics conference. However, I readily accepted the invitation because one, it is rare, another that gives you a platform to express your thoughts. And a teacher would always love to express his thoughts as and when these are solicited, and even when these are not solicited. The International E-Conference on Recent Advances in Physics, a promise to society. The word promise is very catchy. Why we need to make promises at this juncture? Because we are going through a very torrid time. It is a very difficult time for us, both because of the pandemic situation and because of other geopolitical situation, and because of the situation for that we only are responsible. That as far as I can say, technologically, because I am a student of engineering, that we have not got the respected place which we should have got. I would not say at this juncture that we deserve that place, because our ancestors might have deserved that place, but we don't. Today, because of all these things, we are the largest technology importing nation. So that is why, as Indians, we have to make a promise to the society. So that is why I say this promise is a very catchy word. Today are the times when nation requires several true promises to be made by us. So as a guest speaker, my job is to enthuse you so that you not only make promises but also keep those promises. Basically, I'm a student of engineering, as I said, and that is why I consider myself not an outsider to the physics fraternity, as physics is mother of all engineering. And a physicist's promise has to be carried out by an engineer, because applied physics is nothing but it has to have some kind of engineering element. So it is like a Krishna-Arjun relationship, when vision and action both are important, and but in isolation both are waste. So what we need is not only a vision but also a program of action. And mere vision can be a daydreaming, and mere action would be a waste of time. So if you have I don't know if somebody has read Bhagavad, the last slok of Bhagavad mentions Yatra Yogeshwara Krishna Yatra Partho Dhanurdhara Tatra Shri Virjayo Bhute Dhruva Neter Marti Termama. This means that Purna Purushottam Bhagwan Krishna, he represents the divine vision, but the vision alone will not help. And on the other hand, the Parth, the Arjun, the archer, is the man of action. So without vision, he cannot achieve success. So both have to work in tandem. So, well, friends, a promise is a promise, and people with good intentions make promise, and people with good character keep them. So I hope during this these conference days, you are not only going to have good intentions by making good promises, but also you would be in possession of good character to keep them. Why I'm emphasizing on why I'm having a little suspicion that we are not able to keep our promises, though I pray to Almighty that this conference would be an exception, and where most of the promises are to be kept, because we have not been able to build quality institutions, and quality institutions is about people. We have to have hungry students and hungry teachers. The hungry, we are blessed that because of our demographical dividend, we are blessed with the hungry students, but hungry teachers, it's very difficult to find. So it has to be, because teaching profession should have been a most compelling profession in society in every sense, in its richness, in its experience, in its conversation, in its freedoms. Teaching and research both. These professions should have been like that, and possibilities should have been in abundance. Not to mention compensations. So so only the best can bring these institutions back from the brink. Why I am saying brink? Because we can be proud of our heritage. We can be proud of our past richness as far as science development in sciences was concerned.
Yeah.
Bhuvesh sir, he is not audible.
Okay, I think Sachin sir has disconnected. Okay, let's proceed. I think I have to wait. We have to wait. Okay, let's proceed to the next session. Where is my camera? Okay. Now let's proceed further. Thank you, Professor Maheshwari. And you are right. Physics and engineering both are related to each other in many aspects and has very important role for our society. Now, I will ask Professor S.C. Chandola ji to declare this conference open. Sir, Chandola sir.
Yeah. Am I audible?
Yes, sir. Yes, sir.
Can you hear me?
Yes, sir.
Can you hear me?
Yes, sir. I am.
Okay. So the conference is open now to all the contributors and participants of the international conference. Yeah. So should I call the first speaker?
Yes, sir. Yes, sir. It's my time.
Okay.
Now it's time for our keynote lecture.
So sound is not clear?
Yes, sir. It is coming clear.
Wait a moment. Yeah. Is it okay now?
Yes, sir.
Am I audible now?
Yes, sir. Yes, sir.
Okay. So thank you, Bhuvesh, and can you listen me?
Yes, sir.
Okay. Am I audible?
Yes, sir. All are mute, sir, right now.
No. My voice is there.
Sir, your voice is there. Here.
Okay. So we now start the conference. The main agenda of the conference. That in this first session, I'm thankful to you that you invited me to chair this session. And in this session, in this conference, Recent Advances in Physics, a Promise to the Society 2020, I invite Professor N. Nimai Singh. I would like to introduce Professor N. Nimai Singh. He will deliver his talk here. Professor N. Nimai Singh, he comes from Department of Physics, Manipur University, Imphal. He has been ex-head of the department and convener of the physics department at Manipur University during 2017 to 20. And he was at the Guwahati University also as a head of the department from 2010 to 2013. Professor Nimai Singh has done his PhD from Delhi University. He was after his PhD from Delhi University, he joined as assistant professor at the Guwahati University in 1991. Professor Nimai, please correct me if I am not correct. Yeah, thank you very much. He has been a recipient of Commonwealth Fellowship in United Kingdom during the year 1999. 2000. He has been a regular associate of Abdus Salam International Center of Theoretical Physics between 2003 and 2010. He has been General Secretary of Physics Academy of Northeast, PNE. He has been founder member of the Research Interest of Science and Technology, RIST, Imphal. and he is actively engaged in popularization of the science. We salute to Professor Nimai Singh for his endeavor. His fields of interest are high energy physics, theoretical, of course, the quark dynamics, the grand unified theories, neutrino physics. He has published a number of papers in international journals. He has produced more than 15 PhDs. He has written a very nice book on quark model and beyond, The Eternal Quest. I'm right. With this brief introduction of Professor N. Nimai Singh from Manipal University, Imphal, I request him for his keynote address. His topic of the address will be neutrino oscillations and some unsolved issues. And he'll be talking in terms of for Super Kanya-Konde detector for neutrino oscillations, which has got Nobel Prize in 2015 for the neutrino oscillations, right? So thank you, Professor Nimai Singh, for your contributions and accepting the invitations for this international conference. And I invite Professor Nimai Singh for his deliberations. Thank you. Professor Nimai Singh, I think your mic is muted. Yeah, can you please unmute your mic because you are not audible. Your mic is.
Right.
Thank you.
Okay. Can you hear now?
Yeah, I can hear that.
Okay. Should I start now?
Yeah, you can start.
So first of all, I am very happy to express my feelings that I am able to interact with all the experts here. I am very thankful to Professor I.C. Chandola and Professor Sachin Maheshwari and convener Adarsh Kumar Chaudhuri and his team. And now I will start directly, and I also thank all the participants of this conference, beautiful conference, International E-Conference, Recent Advances in Physics, a Promise in Society. Even though I speak on theoretical physics, theory and experiments are related. Today's theory is tomorrow's experiment. So please bear this thing. Okay, let me start directly. Can you see now? Hello?
Are you sharing?
Yes, I am sharing. You can see now?
No,
sir.
No, sir. How to share?
Can you please open the option?
Oh, now I will do present now. Okay, I will click on present now. Present now. Okay. Okay. Share. Okay. 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 Can you see now? Hello. Can you see my slide?
Yes.
So now I will start. This is my first time in e-conference. This is why. Okay, please excuse me. Okay. So today I am speaking on neutrino oscillation and some unsolved problems. Okay. So to start with, when we talk about physics, we have three things. That is our mind, consciousness, and the physical world. That we have to understand what is the physical world. The apple falling is the physical world. After that, in order to explain the physical world, we should have the mathematics. Whatever things we have in physics, we should be able to explain with the help of mathematics. So mathematics is the language of physics, and the mind, physical world, and mathematics is called eternal triangle. So it is a synergy. Okay, that is what I believe. Then the next step is I just want to summarize the development of the physics. When we have a cube, this is cube of nature. When we have a cube formed by three constants: gravitational constant, Planck constant, and the velocities of light, the starting point 0 is called the Galilean physics. Here there is no gravity, no quantum mechanics, no relativity. This is called the Galilean physics. When this Newton's gravity and the special theory relativity mix up, we call another theory called general theory of relativity, which does not have quantum mechanics, but it has gravity as well as relativity. On the other hand, in the 21st century, when there is a marriage of quantum mechanics and relativity, we have a new theory called quantum field theory. Quantum field theory, we don't have gravity here. Neutrino physics will come into the quantum field theory. But everyone knows that a true theory of nature should encompasses gravity, relativity, and quantum mechanics. So people are looking for this theory. So far we have the theory called superstring theory. This theory, we suppose that it can explain gravity, quantum mechanics, and relativity. So this is a brief idea how the conceptual development in theoretical physics occurs. This is we call the cube of nature. Now, before I start my topic, let me point out that in the last 50 years, all the major branches of physics in the basic sciences, they merge. Particle physics and accelerator physics, general theory, relativity and cosmology, space technology, astronomy, planetary science, so Hubble telescope, NASA, COBE, WMAP, LISA, Planck, these are satellite. Biology, origin of the life, computing, electronic, mathematical science, data-enabled science, big data, computational physics, artificial intelligence, physics. And so these are different branches. These branches are interlinked. These the connectivities of the major field of studies. For example, particle physics is related to the cosmology. When we talk about the cosmology, the Big Bang theory, we have to explain through particle physics. These are related. Similarly, cosmology is related to space science. So in order to study cosmology, we need space science. In order to have space science, we have the computation and robotics. So in order to have the origin of life, we should have the quantum mechanics. This is anthropic principle initiated by Schrödinger. So genome, in order to have the genome problem, we have to have computation. So these are interlinked. So what I want to say that in last 50 years, all the major field of studies are connected. So in one way, there is separate branches of physics. All the physics branches will be connected one another. So this is called the connectivity of the major field of the 21st century. Okay. So this is a brief map about what we know, what we are going to do. So say quantum, so there are many places where they have matter, antimatter, asymmetry, this grand unified theory, M theory, superstring, the higher dimension. So these are the places where we have to find out. These are places we have to find out. So this is a brief map about what we have done and what we are going to do in physics. Okay. So coming to neutrino physics, let me point out some puzzle from heaven. So now we know the Big Bang theory, but what is the origin? What is the mechanism for the origin of the Big Bang theory that we are still looking for? So then just after the Big Bang, there is the inflation. What is the mechanism of inflation? That is we are looking for. Then antimatter-matter asymmetry of the universe via CP violation. That is we are working for, we are looking for. Nowadays, we have very high 10 to the power 19 electron volt cosmic rays. From where these cosmic rays are coming, how they are formed, it is a puzzle now. We have dark matter. Dark matter, as you know that, it is which cannot be seen by telescope, okay, but they have the gravitational pull. Dark energy, which have an anti-gravity effect, which help in the expansion, accelerated expansion of the universe, and the solar and atmospheric neutrino physics, gravity wave. This is the area where I am going to emphasize, and these are related with all these things. Okay. Now we know that the universe is more than around 70 to 75% are the dark energy that is anti-gravity effect they are having, and they are a pervasive medium. Okay, they help in the accelerated expansion of the universe. Around 27% is the dark matter, which we cannot see by our telescope, or okay, they are immune to light, they are chargeless. Okay, 30% is our ordinary matter, that is we know already. So this is another graph. Now, when I talk about the new physics means which is beyond the standard model of particle physics. Standard model means electroweak, symmetric, electromagnetic, weak, and standard strong force. These three unification is called standard model of particle physics. What is beyond the standard model, we call it is the new physics. Neutrino physics is neutrino mass is new physics, dark matter is new physics, dark energy is new physics, supersymmetry is new physics, proton decay is new physics, string theory is new physics. So my topic is neutrino physics. Now this is the famous graph of Vera Cooper-Rubin and her collaborators to find out the existence of the dark matter. It is the rotational galaxy. Experimentally, it should be done like this. Theoretically, it should be done. It is the experimental. It means that far away from the galaxy, center of the galaxy, we have a lot of matter called dark matter. Okay, that is the famous M33 rotational curve of Vera Cooper-Rubin, who died recently in the last 1 year. This is the famous picture of WMAP, where there is the accelerated expansion of the universe. This is the inflationary, it is the accelerated expansion of the universe, because it was given the Nobel Prize. Okay, so we are going to find out the existence of dark energy for the accelerated expansion of the universe. Still, we are going to find out, but for this observation, Nobel Prize was given. Okay, so now, in this talk, I am confined to neutrino oscillation. So to start with, let me start from the 2015 Nobel Prize in Physics. 2015 Nobel Prize in Physics was devoted to two persons. One is Professor Takaaki Kajita and Professor Arthur MacDonald. So these two, Professor Kajita, the Japanese fellow, he was the leader of super kamiokanda in Japan for the discovery of the neutrino oscillation, atmospheric neutrino oscillation. And Professor Arthur MacDonald, he's the leader of the Sudbury Neutrino Observatory SNO in Canada. So the implication is that neutrino can oscillate between the two species, from electron neutrino to muon neutrino, from muon neutrino to tau neutrino. In ordinary physics, standard model physics, they cannot oscillate, they cannot change. But here, it is found that they oscillate. This is why it is beyond standard model, it is a new physics. This is Professor Kajita and Professor MacDonald. Okay. So, as I told you, in neutrino oscillation, from one flavor to another flavor, it is a quantum mechanical superposition when the neutrino travels, it picks up a phase. Okay, a phase. So it is the quantum mechanical superposition that I will explain in future. Okay, so neutrino oscillation is one of the hottest topic in physics, both from theory and experimental front at the moment. Okay. Okay. So now the significance. Now the neutrino oscillation is so. Hello, can you hear me?
Yes, yes,
Hello?
yes.
Yeah, okay, okay. There is some, so now the neutrino oscillation is the example. The neutrino oscillation, there is the vibration of lepton number conservation. In neutrino oscillation, there is a lepton number conservation, okay, that is beyond standard model. So in neutrino oscillation, there is high possibility of CP violation also, and it may explain the matter-antimatter symmetry of the universe. Okay, so
Nimai sir, you are not audible. Your mic has been muted. Nimai sir, Professor Nimai sir, your voice on.
Please unmute your mic. Yeah? Professor Nimai, please unmute your mic.
presenting. Yes, can you hear now?
Yeah.
Okay. Okay. So now, what I want to, can you hear now, please?
Yeah.
Okay. So now, if in this neutrino oscillation, if lepton number is violated, there is a possibility that neutrino may be Majorana particle. Majorana particle is particle and antiparticles are the same. Okay. So this is the classification. We know that. So we have fundamental forces means those vector bosons, leptons, and quarks are the fundamental particle. Okay, fundamental particle. So we have neutrino. Okay. So this is the fundamental elementary particle. We have 6 quark. We have 6 leptons, and this neutrino, we have 3 neutrino, 1, 2, 3, electron neutrino, muon neutrino, tau neutrino. This is the chargeless lepton. Okay, so they are massless in a standard model, but others are having masses. Okay, so in brief history of neutrino, we know already. I will skip. It started from James Chadwick in 1914 because neutrino beta decay should be a continuous. In order to explain the continuous, we have brief neutrino history. We starting from Wolfgang Pauli, Enrico Fermi. We have in 1956, neutrino was first discovered, electron neutrino, antineutrino. In 1962, muon neutrino was discovered. So in 1968, so in 1987, neutrino from supernova were detected. So in 1998, okay, the atmospheric neutrino oscillation by superconductor were confirmed. Okay, so in that way, in 2002, okay, so this is the history of neutrino. So now this gentleman Joji Totsuka, he was the leader of Super Kamiokanda, but before announced before getting Nobel Prize, he was dead. So he was replaced by Kajita. Okay. Okay. So now another hero is called Bruno Pontecorvo. He proposed the neutrino oscillation. So in 1957, Bruno Pontecorvo suggested the neutrino oscillation, and it was extended by Maki, Nagagawa, and Sakata. So this is then it was modified by Gribov, Wolfenstein, and Mikhail. This is we call MSW effect. Okay, this is solar neutrino. So when we talk about the solar neutrino oscillation, we call it is MSW effect, because when neutrino come out from the sun, it interacted with the electron gas, and it gives the maximum neutrino oscillation, maximum mixing. Okay, that is called MSW. We call MSW resonance effect. Okay, so let us come to the neutrino sources. So when we discuss about the neutrino, in Big Bang theory, we have a large number of neutrino. Like cosmic microwave background, we are believing that there is the neutrino microwave background, neutrino background. So it will give, study of neutrino will give the understanding of Big Bang theory. Solar neutrino, because sun produces through thermonuclear reaction, by thermonuclear reaction, okay, by fusion of proton, it makes helium nucleus, and finally it produces neutrino with the energy about 26 MeV. So it is solar neutrino. From supernova explosion, it also gives neutrinos. The energies are different. Okay, we have atmospheric, from cosmic ray, finally from cosmic ray, finally we have electron neutrino and muon neutrino, and from high energy cosmic ray 10 to the power 12 to 10 to the power 19, okay, electron volt, cosmic ray sources, neutrino from the earth inside also. So nowadays, in order to investigate the geological investigation, we use neutrino, because neutrino can penetrate inside the earth. Okay, so these are the sources of neutrino, but artificially we can also create accelerator neutrinos, we can create reactor neutrinos. These are the different sources of neutrino, and we have different energy for these. Okay, and we have different energy. So let us come to, so my timing is off. Should I continue for another 5 or 10 minutes? Hello? Hello? Hello?
Hello.
My timing is up. Should I continue for 5-10 minutes?
3 minutes, yeah.
Okay. So
Thank you.
Okay. So it is the beta decay. It is the beta decay. So we have, this is for quark part CK matrix. This is the quark. This is the neutrino part called PMNS matrix. Okay. So I will jump about. So it is the theory of neutrino oscillation. In order to have a neutrino oscillation, we have the this is called, we eigenstate nu1 and nu2 are called mass eigenstate. It is a hypothetical eigenstate. So there is a rotation. Okay. In one way, the flavor eigenstate is the mixture of the weak eigenstate. Okay. So when it travels, they pick up a phase, and this is responsible for the neutrino oscillation. This is the formula of the probability of neutrino oscillation from electron neutrino to muon neutrino. It depends on angle. It is called solar angle, and it depends on the difference between length from source to observer. It is the mass square difference between m2 square minus m1 square. It is the energy of the neutrino released from the source. This is for atmospheric neutrino, from muon neutrino to tau neutrino. And so it is the angle, atmospheric angle. It is the m3 square minus m1 square. It is the energy of the atmospheric neutrino. It is the distance. So this formula is very important formula. It is a derivation. So I won't speak about much about. So this is the it is a Nature, in a Nature publication. When the electron neutrino oscillate, at some point of time it becomes the muon neutrino because it is composed of nu1 and nu2. So with time the composition will change, so it becomes nu2. So it is from the source, it is from observer, it is the neutrino oscillation. Okay. In the neutrino oscillation, we have three angles. It is the first generation, 1 and 2. It is the solar, it is the atmospheric, it is called the reactor angle. This is very small. This is why if we neglect this one, it is almost zero. This is delta is called the Dirac phase. It gives you CP violation. If delta is different from 0 and pi, it is called CP violation. Recently in 2012, 2020, K2K in Japan, there is evidence of the CP violation, but it will be repeated again. Okay. So CP violation in neutrino sector because delta is different from 0 and pi. So this is the eigenstate. Eigenstate. It is the mass eigenstate. It is the three angle. It is the Dirac CP. If the neutrino is Majorana, it is called the Majorana phases. Okay. So but we have in neutrino 9 m1, m2, m3. The mass, 3 mixing angle, 1 phase. Dirac phase, 2 Majorana phase. These are observable, and you know, absolute neutrino mass, we had tritium beta decay, neutrinoless double beta decay, cosmology. The absolute neutrino masses can be measured from these three also. So these are the experimental things. This is a brief idea how neutrino masses are observed. It is the kinematical test, cutting, and it is a cosmological WAP, and it is the neutrino oscillation. It is the double beta decay in the neutrino oscillation, artificial source, natural source. In artificial source, accelerator, fusion, neutrino beam. In the natural force, solar and atmosphere, long baseline and the short base. All the neutrino experiment will fall inside this mid. So I don't have much time. So now, finally, what I want to say is that in Super Kamiokanda, so atmospheric neutrino oscillation was observed and confirmed by using water detector, pure water detector. Okay, pure water detector, and in atmospheric. So atmospheric neutrino is, so it depends on a zenith angle. It depends on a zenith angle. It was exhibited, okay, and this is the cosmic ray. So this was observed. This is the cosmic ray, how neutrinos were produced. Okay, so this is a zenith angle dependence. So they have observed. It is the Super Kamiokanda observation. I won't speak much about. So it means that from Super Kamiokanda we conclude that muon neutrino change to tau neutrino, and these are the measurements. The mass square difference m3 square minus m2 square is about this. in this range, and the mixing angle between these is range. So it was confirmed later on by many others also. So it was directly confirmed by Opera and others, K2K minus T2K and Antares IQ. Okay, so they were given the Nobel Prize. In the case of the solar neutrino, as I told you, 4 proton max inside it is nuclear fusion. Fusion means inside the sun. Okay, about 27 MeV is produced. Okay, so I won't speak much about. There are 4 reactions inside the sun. Okay, so in the case of the snow, we cannot use snow means Sudbury Neutrino Observatory. So that Harvard was seen proposed that we cannot use pure water as a detector in order to identify that where the neutrino has gone. Okay, so in order to find out where the neutrino has gone, in which neutrino it has been rotated, we have to use the heavy water. So use of heavy water in snow was first proposed by this Shane, but after this proposition, he published a paper in PRL and he died, and it was later on introduced. Okay, so using the heavy water, we have 3 reactions: charge current reaction, neutral current reaction, elastic scattering. If we use pure water, we have only elastic scattering, but if we use heavy water, we have neutral current, CC, and elastic scattering. So if we use heavy water detector, we can find out muon neutrino deficit from where it has been oscillated. It is found that it has been oscillated to tau neutrino. So electron neutrino has been oscillated to muon neutrino. It has been found with this heavy water detector in snow. So I am giving you all these reaction. Those people who are interested can these are the different reaction. Okay, different reaction. So this is the snow. So okay. So what I want to say is that so now this is a new. There are so many new experiments. Okay, one is hyper Kamiokanda in Japan. Super Kamiokanda will be upgraded to hyper super Kamiokanda in Japan. So this is thing. Now what I want to say is that these are unsolved problems. Even though we measure the mass square difference of the neutrino, we don't know the masses, individual masses, M1, M2, M3. So M1, M2, M3, the absolute neutrino masses we don't know. So this is one problem pending. If M2 is always greater than M1. So M3 is greater than M2, M2 is greater than M1, it is called normal ordering. And it is also possible that M3 is the smallest, M2 is greater than M3. This is also possible. It is called inverted hierarchy. For the same mass square difference, we have 2 possibilities. So we have to find out the mass ordering or mass hierarchy. So this we don't know. We have to find out the CP violation in neutrino sector also. We have to find out neutrino is Dirac particle, which is different from particle and antiparticle, and a Majorana particle or self-conjugate particle, which is equivalent to its antiparticle. And there is some experiment called LSND and others. They find that not more than three varieties of neutrino they have indicated that. So that is called sterile neutrino. From CERN experiment, only 3 neutrino varieties are possible. So sterile neutrino is extra neutrino which do not have interaction with WZ boson. We call sterile neutrino. Existence of sterile neutrino, 4th or 5th or 6th varieties of neutrino. It is the present experimental things. Okay. Now,
Professor Nimai, time.
oh yes, now I am finishing now.
Okay.
Okay. Let me complete. Yes. Let me complete last line. In India also we have one experiment called India-based neutrino observatory INO. So we are trying to catch up and compete the entire world. Also, it is INO. So it is in near Madurai, Bodhi West Hill, and India-based neutrino. It is Myon neutrino. Okay, so those interested people, please find out. So if we are lucky, we can find out some of these some pending problem in neutrino. So these are the agenda of INO neutrino. We want to find out atmospheric neutrino, hierarchical CP violation, and many other things. Okay, okay. So lastly, I want to point out this picture because Emperor's New Clothes. This means that young people, unlike me, young researchers, young people should have a gut to question the existing theory. Okay. So they should be able to question the existing theory, whether it is right or wrong. Only then new science will come up. So this picture is very famous. I borrowed it from Sargent Nalikar's paper. Okay, thank you very much. Okay, I could not present up to the satisfaction. Time constraint. Thank you very much once again. Okay.
Thank you, Professor Nimai. Thank you for your illuminating lecture on neutrino oscillations. And yes, that's why I told the people here think differently. Yeah, that's how the solution to the problems it comes. It is a very hot topic nowadays, the neutrino oscillations, and you have it cannot be done within a time slot of half an hour. You need more time, I understand. So far as these neutrino oscillations are concerned, does it make possible these neutrino as a candidate for the dark matter?
People are thinking of, but still there is no, still it is possible, but still, but neutralino in supersymmetric particle is the axion and the neutralino are the candidate. But neutrino, it is ruled out nowadays. Slowly rule out neutrino.
Okay.
Hello, sir.
Okay.
But supersymmetric particle called neutralino and axions are a strong candidate for dark matter at the present.
Okay. I open the session for the discussion. Any question from the audience?
Okay, I will send my transparencies and you please study. Okay, in detail. Okay.
Thank you.
Okay, please distribute my transparencies to all the.
We have recorded your lecture, so we will distribute this lecture. Yeah.
Thank you very much.
Thank you, Professor Nimai, for your illuminating lecture. Thank you very much, and we hope more contribution, more collaboration later on also. So we thank you, Professor Nimai, and now I invite Professor. Just a minute. Professor Durgesh Rai. Professor Durgesh Rai, can you listen to me? Professor Durgesh Rai. Professor Durgesh Rai, can you listen to me? Are you in the conference? Hello? Hello?
Hello.
Professor Durgesh Rai. Yes. There is loud humming coming in your mic. Yeah? Professor Durgesh Rai, can you listen to me? Yes, Professor Durvesra is with us. And so our next speaker will be Professor Durgesh Rai. Let me introduce Professor Durgesh Rai. He has done his post-graduation from Banaras Hindu University. He comes from the solid state physics, I mean condensed matter physics, and he joined later on he joined IIT Kanpur, and he did his MTech from IIT Kanpur. He later on moved to United States for his PhD, and he got it there from the University of Cincinnati, from Department of Chemical and Material Engineering.
Hello.
Am I audible?
Yep. Yes, yes, you are.
So he did his PhD from United States University of Cincinnati, and from Department of Chemical and Material Engineering. He he had been postdoc at Oak Ridge National Lab at MIT, Massachusetts Institute of Technology, and he was a senior scientist in Oxfordshire in United Kingdom. His work is on X-ray and neutron scattering, and today he'll be talking about a glimpse of fundamental and applied physics aided technologies for current and future health research. So this has something to do with the health research, and in the era of corona pandemic, this lecture seems to be a very useful lecture. Yeah, Professor Professor Durgesh Rai, can you please start your deliberation?
Okay, can you see my screen?
Yeah, we can. Yeah,
Great.
Thank you. Yeah.
All right. So I will try to manage it within half an hour. That's my goal. We'll see how far I can go.
Okay, that's right. Yeah, thank you.
Okay. So the idea here is that I wanted to, as you correctly stated, a glimpse of how modern technologies come together to help with fundamental research in healthcare physics. My training is in physics, so I see things as a physicist. And I want to present two aspects. First, how instrumentation is approached from basic principles of physics. What are the challenges of first principle physics in when it comes to industry for a 24/7 operation, how you actually deal with that, how you optimize instrumentation for that kind of an operation, and I'll give some glimpse of basic biophysics, again suitable for physicists for most of it. And then the idea is that I'll actually shift gears towards some imaging. I'll show you how it is done. And then the idea is I'll give, at least if not by slides, I'll basically try to tell you how modern technologies and progress in image processing is going to be very helpful. We all have, for example, our Android phones. They all are very good at image processing. So
Durgesh, Dr. Durgesh, please unmute yourself.
You are muted, Professor Durgesh. You are muted. Please unmute.
Durgesh, unmute. Dr. Durgesh, please unmute yourself.
Professor Durgesh, you please unmute your mic. Yeah? It's muted. Professor Durgesh, can you please unmute your mic?
तो अगर इस वजह से मैं अपना ऑडियो खोलूंगा ना तो मेरा भी सुनाई देगा ना।
Dr. Durgesh, please unmute your mic. Dr. Durgesh, can you please unmute? Your audio is not coming here. Hello. Dr. Durgesh, please unmute your mic.
Someone please call him on his phone, on his mobile. Someone please call him. How about that?
Okay.
Now,
Others, please call him.
can you hear me?
Yeah.
Now
Can you
it is
get-
Now you
working.
are audible. Yeah. You are muted. Now it's audible.
Oh, okay, so I'll repeat everything I said.
Okay.
All right. But you can see my shit. But you can see my screen, yeah?
Yeah. We can. Yeah.
Oh man. Well, let me reiterate what I was saying. So the idea behind the talk is that I want to give you a glimpse of fundamental research that is being done using applied physics in the healthcare research. I intend, here's the layout. In the interest of time, I'm going to talk mostly about how do we optimize high-process SAC cell, and then I'll try to integrate a glimpse of a couple of approaches for COVID research in the perspective. I'll then go and talk about some neutron optics and scattering. The idea was to tell you guys that, imaging, or for that matter, any 2D data is very efficiently processed by machine learning algorithms because they work on a matrix basis. So as a result, you can actually, have a Fourier transform of a live 2D image live. So it's that efficient. Your cameras actually do a lot of machine learning algorithms on the go. And it has all to do with how it's implemented by a matrix process. And if time persists, I will elaborate more on the on how neutrons and imaging actually can couple together with other instrumentations and learning algorithms, machine learning, and hopefully deep learning down the road to predict different problems in health and use to diagnose them. So with that, I'll give you a very brief understanding that the whole purpose here behind this talk would be to elaborate how instrumentation suits are going to be made, for example, for neutrons, which will depend on neutron characteristics and optics, sample environment, and detector geometries all coming together to present a perfect instrument for a particular problem. I do not foresee that I will have the time to elaborate on the problems, but I will give if I don't have this time, I'll just give a very brief overview of where we are going. And it is important to understand that the whole X-ray and neutron and synchrotron, one of the limiting factors has been that the user base that exists in this world actually is largely based on experiments that are actually conducted in the lab. That's how the specialty actually grows, and no matter how capable your instruments are, if you don't have the right user base which can complement your resources, it doesn't really work to the magnitude it could. So we are looking into that direction as well, that how we can use computational as well as complementary techniques to better showcase the capabilities at neutron and synchrotron sources. So I will discuss a little bit about high pressure biology. As a physicist, physics pressure is very important to me because you must have heard of temperature denaturation and all kinds of physics, but pressure is not done largely because of problems with instrumentation. They're just not available in the world. They're kind of very difficult. So that's the problem we are trying to solve. And even if you actually build an instrument, it has to be user friendly. Until you actually make it user friendly, your capabilities do not really matter. So before that, I will briefly introduce you to why we do this. So life actually exists under pressure a lot. There are deep sea hydrothermal vents, couple kilometers deep, where sunlight doesn't reaches, but there is very active life. The Pacific viper fish, they go 5 kilometers. And then I'm sure you might have heard of micro animal called tardigrades, which can survive 60-kilometer deep water, which doesn't even exist, but 6 kilobar pressure. It actually exists in space without, under radiation conditions, very low temperatures, and it's very difficult to kill. So we'd like to understand how these things work, and then it's all about also the origins of life, the limits of life. There are lots of biophysical problems to be solved. To provide those which do not have a background in biology, like myself, let me give you a very simple example. Is that proteins are like, you make your hand, okay? You have like 5 fingers, you actually make a fist, and that's how proteins are. Basically, they're a combination of, they're like your fist, consisting of your palm and 5 fingers. If you notice your fist, you'll notice that there are curvatures on it. And in fact, if you actually have some sand and you put it inside your fist, you will see you will be able to capture some even when you actually close it all the way. And that is because there are cavities inside our fist, and the same way proteins have those as well. And they are very essential. They are very essential for enzymatic reactions. They are hydrophobic regions, and typically they're very essential for human existence. And so it so happens, at least under pressure, is that you have these cavities, you apply pressure, and then the water kind of goes into these cavities and it unfolds. If you notice that, you might come to the sense that the water actually goes into the hydrophobic regions, all right? Now, if you heat this protein, the interaction with water with the protein actually happens in the hydrophilic areas on the surface, for example, as you can see in the image. On the other hand, the pressure actually affects the hydrophobic regions. So in a lot of ways, they are very complementary in nature. Nonetheless, this should give you some basic ideas of how it works. Now, if you understand that, let me give you an example of a COVID research that actually is being done as of today and going into tomorrow, day after tomorrow, at our beamline. So it's called glutaminase, GAC, if it's or GAL, depending upon if it's from liver or cancer. So this is very common cancer-related protein that has been widely studied. If you notice, the inhibitors are right in the center, and if it's actually a tetramer. This is basically 4 proteins stacked together in a way, and there is gap right in the center, and that's where all the reactions actually happen. If you actually apply, look into calculate the empty volume, you will actually quickly realize that this red, blue, and green actually denote 3 of the largest cavities inside this particular protein. So that kind of shows you how critical pressure is. You actually apply pressure and you can actually modulate the experiments that are going to happen tonight, not tonight, then certainly tomorrow and after tomorrow. It's our actually synchrotron is open for COVID related research. So with that introduction, let me also show that this is not new. It has been already been proved that using pressure you can actually change the activity of virus, because virus actually, if you look into their structure, they have a lot of open space in themselves for them to basically act. So this has already been proved. It has not been widely used, but this is the kind of approach we are taking. One approach is using the GAC. The other approach is directly on inactivating the virus. If you look into the author list, there is this guy, Gerson Silva. Gerson is in Brazil. Recently, I actually had to get his. I had interactions, and he actually suffered from COVID himself. So he's also prospectively looking into a proposal in this direction. Anyway, so with that, I'll shift gears and show what we do with the small angle scattering. So in small angle, we could have light, you could have neutrons, you could have X-rays, whatever, you basically need a beam or a wave. You actually shine your sample. When you shine it on your sample, it will scatter because it will interact with the sample. It so happens that the angle we call reduced angle is denoted by a wave vector. Essentially, the wave vector is to normalize a geometry, because you can have different distances, but the wave vector Q can normalize all kinds of geometries. You can compare Q directly. If you calculate theta, for example, that we are generally used, intensity versus theta, that depends on the wavelength. But if you actually plot as a function of Q, it's independent of vacuum and, for that matter, any geometry. So that's what we generally use in small angle scattering. Most of people are, very familiar with what we call XRD, X-ray diffraction, which is at the higher angles, structure factor, interatomic structure correlations. Small angle generally happens in much lower Q at much smaller angles. And in the low Q, we look for what we call form factor, or the shape of the molecules, more than the interactions between those molecules. Although in principle, we can actually look at those interactions as well, but that's a different story. We typically look at form factor. The most important thing is to get the size from RG, as you can see in the curvature, and look at how dense the whole aggregate is. It's very good in biology, at least it's very good efficient for flexible peptides. You can acquire data in a matter of seconds. It's very economical, and you can look at tertiary structures and then complement with secondary structures from, let's say, any spectroscopic methods, IR, or any spectroscopy for that matter. With that background, I'm going to go directly into the instrumentation part of high pressure design. So the underlying principle is that it uses what we call Bridgman seal. And before I say Bridgman seal, let me say any O-ring works on the principle that force is pressure by area. Okay, so you actually reduce the area using an O-ring. So as a result, the pressure on that O-ring becomes much higher than the area on the whole surface, and that is how O-rings work. In Bridgman seal, you basically use an O-ring with a backup ring. This is how the technical layout looks. You basically have 3 Bridgman seal. The X-ray goes through one window, comes out of the other window. Then the sample is changed from the top, okay? And the whole hydrostatic pressure that's created inside is actually locked against this bolt lock mechanism that you can see, that you can slide in and out. This is how if you actually keep this, on the sides and remove the main block, this is how it looks. What you should note is that, well, you should note that the diamond, well, let's see.
Excuse me, sir.
Yes.
Kindly make screen visible.
Make things visible. Well, it's kind. I'm sorry for that
No,
because
no.
Make this.
It is visible. You can check the design screen presentation by Durgesh Rai. It is visible, and you can pin your screen in that. Please, sir, continue.
Okay, sir.
okay. Yeah, I'm sorry for, but it's kind of tricky to change in the middle for obvious reasons. So so the idea is that the way it works is the diamonds are actually seated on these two seats on either side, and in the initial design, which was very sound first principle physics design, the diamonds was pressed against the surface using two springs, metallic springs that you can see in sort of yellow in this figure. I don't know if you can see my cursor. And these two are then pressed against this blue spacer in the center. And this is fine for general lab purpose. But when you actually use on a synchrotron 24/7, or for that matter, any neutrons or industrial application, then things are going to go wrong. And when things are going to go wrong, they have to be repaired fast. Okay. And this is just not a design that could be repaired fast, even if it is actually just a good design based on first principles of physics. So we had to make some changes. Once we realized that we couldn't swap up parts as fast as we like, we had to make some changes, and that's the next part. It's sort of difficult to show in the figure. I don't think I am doing justice to the part, but let me show what the idea is. The idea is that instead of things, getting correlated, which is the pressure on the diamond is because they're both pressing against this spacer in the center, we actually designed ourselves or redesigned the seats in a way that each of these two sections on either side is basically an independent system. Okay, so this way you get the advantage that you basically have your seat, your O-ring, the diamond which is shown in black. It should certainly have been shown in white, but then white against white you can't see. So the thing that is black is the diamond. And what this enables us is that it enables us a modular configuration. And what I mean by that is that if there is anything that goes wrong in one side, you just kind of swap it instead of having to redo the whole assembly. Thereafter, this is how it looks. We actually put some bracket on the outside. So what this enables us to do is that it actually enables us to put vacuum and further optimize our background. We then worked on enhancing our mechanical stability to make sure that we have better positional and predictability. This is again very important. Biological samples, organic samples are not great at scattering. Okay. We are kind of carbon. So anyone who has done EM and EM know that organic matters are not great for contrast using, for that matter, any most techniques. So us being carbon and like plastics mean that we have to be very efficient to get good data statistics. So then we came up with particular set of stages, low profile stages that provided extra stability, thermal jackets that's great for temperature equilibration. And in addition to that, we were able to get a vacuum line operational, and this actually mates to the vacuum. And that is something that I'll show in the next slide. And this was very stable throughout the operation. We didn't see much issues with reproducibility of our data. Then the next thing is that everything works. Now let's optimize the path length. Okay, what do we need for that? We need just the right thickness of diamond windows. The thicker you get, the more is your background. So you want to actually optimize your background as much as possible, which we did using a special kind of diamond called HPHT, high pressure, high temperature diamond, sourced from Russia. Then we optimize what we call attenuation length, which is basically as X-rays travel through your medium, they get absorbed. So you just need the right, to get the best statistics, your attenuation length should be equal to your path length, and that both equal to 1 by E, which is so we can match that. And lastly is the transmission. So we actually calculated the transmission for the whole setup, and we optimized these 3 configurations to get the best statistics, and that I'll come later. This is how it looks on the beamline. You basically have detector, Eiger 4M detector, and then this cell, which we use a couple of transducers to measure it. And then, this looks fancy, but what it says is this is how it looks on the beamline. We have everything automated, and you can actually get your data from the comfort of your data acquisition room. Some of the results, I'm showing glucose isomerase standard for those who are not, again, from biological background. This is basically about a 43 angstrom size, 34 angstrom size of protein, 20 kilodalton or so. It's kind of large protein. And what we did was we did this experiment under different pressure conditions, and as you can see, the reduction in the intensity is because, if you understand, protein is more like steel. So when you increase the pressure, on the other hand, water is very soft. Water is basically 90% air. The hydrogen and the oxygen, H2O, only take about 9 to 10% of the actual volume. The rest is basically air in water. So when you actually apply pressure, let's say about 4 kilobar, then the reduction in the volume of water is of the order of, say, about 20% or so, 18%. So what happens is the contrast actually comes from the density of the air in the water and the protein. Okay. As you increase the pressure, that extra air in the water actually decreases, and as such the contrast actually decreases, and that's why you see a reduction in the contrast. A lot of people in biology like to plot what we call IQ square versus Q. This gives a good indication of if the protein is folding or there is something wrong going on with it. In this case, the idea is not to show you folding or unfolding. It is more to show you the statistics, to convince you that the statistics from even a high pressure sacks or diamond windows, which actually aid to background, can get very good scattering results, statistics. That is basically my postdoc job. I'll then, how much time I have? Not much, right? So I'll quickly go over optics, switch to optics. So hopefully this gives you, some idea of how small changes in instrumentation actually all come together to give very good statistics even from biological samples. This is our cell is the only one in the North America. There is one in Europe, one in Japan. If you have any problems that you'd like to work on and you think Preser could be useful, please let us know. I will then go to neutron optics. Here, there's a camera and there is a microscope. A camera generally works that you have a source, you actually let light through an aperture, and then you actually image it. On the other hand, a microscope works on the principle with a mirror or a lens, and then you basically get a magnification based on the distance between the object to mirror or lens and mirror to your image. In this case, I'm trying to present my results on neutrons. The basic principles of this particular, what we call Volter optics, comes from the Chandra observatory, which you might have heard of. So the Chandra observatory basically uses these optics to get image X-rays from distant places. The same principle can be used for neutrons. That's what I did at MIT. It has a lot of advantages. It's great for large neutron sources, collects large solid angles, easy to nest. And then you actually get pretty high brilliance, and you can actually get a lot of gain because of that aspect. Working principle is HPPH is hyperboloid, paraboloid, paraboloid, hyperboloid. Okay, so you have your object placed at the focal point of the hyperboloid. Then the beam seems that it's coming from its image, as you can see, and then in the paraboloid, it's such that this image is actually located at its focus, and so the beam becomes parallel. And then basically it's an even reflection on the other side, so you get an image of your object. The brilliancy of this method is that you can actually vary the focal length, and you can actually change these distances to get various magnifications. You can also collect a lot of solid angle because you can actually nest all these mirrors. This is how it actually looks in the schematic. Basically, for at least simulations, you use graded samples, and you can actually place a large beam stop, and that enables you to basically use, for that matter, any kind of detector. Even CMOS detectors are fine. And this is the beam characteristics. Monte Carlo versus MaxSTAS distributions, they can match very well. MaxSTAS is the package in which all the simulations is done. On the right, you see the divergence. It is very particular. I don't think I can go into details. What is important to see is that you actually gain a lot for a smaller sample, and not that much for large sample. Okay, and let me elaborate on the reason. The reason is that any lens, any mirror, they all have a focusing spot. So the closer you are to that focusing spot, the more gain you get. If you're looking into much larger objects, it doesn't really matters all that much. So that's what I'm trying to show here, that the gain is actually all about the size of the sample. For a smaller size, you get a lot more gain than larger sizes. The whole optimization was to be done for 1 inch sample, about 2.5 centimeter. And the idea was that we should be able to get under 40 micron of resolution. Let's see how we done. So we use circular grid. On the left, you actually look at the sample. On the right, you look at its image. you can see that, this is a 2D. In a 3D, you will clearly see that the color should actually demonstrate that the center is way more higher and this is where a lot of so I have about 2-3 minutes left. Resolution versus distance. So the resolution is, this is distance, different positions of the detector. Okay, so most of the detectors that exist in the world happens to be flat. They're all two-dimensional flat detectors. CMOS, or for that matter, any detector. And that's a problem for particularly for optical. If you have a lens or you use a mirror, the reason is that all lenses have some kind of a curvature to them. What I mean by that is, as you actually go off the zero, the center, there is certain point or distance where the resolution is the best, and that's what is actually shown here, that when your detector is at the zero position, it gets really good resolution, okay, at the center, but then it kind of deteriorates. That's what is shown in the blue line. In the can line, at the detector position of 1 millimeter, it's not that great at zero, but nonetheless, within about 2 inches of diameter, you can remain under 40, a resolution of 40 millimeter. And that's what we were trying to do, that within 1 inch of size, we should be able to get about under 40 micron resolution. But this is where the machine learning and everything is going to come into effect. And the way it's going to come into effect is, if you actually want to study, let's say, you're trying to image the whole brain, right? Most of the recent research is being done in the field of instruments, tools that are actually trying to read the neurons. Basically brain assisted technologies. So they are basically electrodes of different sizes that go into the brain. They then can read the signals that are coming from the neurons. The sizes of those electrodes, the depth of the electrode is what is being researched. You have to optimize all your parameters. So if, for example, if you're looking in on a larger, if you're trying to image your brain, then you want like an inch by an inch sample size. You can use, let's say, if your machine learning algorithms are strong, then your machine should be able to understand that for this inch by this inch, you need your detector at a particular position, if at all it is not curved. In fact, ideally, you should have a curved detector for best results. But the machine is supposed to understand where the detector should be for the result, for the size of sample that you're trying to sample or trying to image. At the same time, once it acquires the image of, let's say, 1 inch by 1 inch, and it sees that there are spots which are of interest, it should then be able to accordingly optimize both the position of the or the position of the sample with respect to the beam, and then so that will work with a little bit with the coordinates. It has to understand the coordinates with respect to the image plate. Then it has to figure out where how to move that sample to actually best showcase the capabilities of the instrument, or for that matter, it's not about show business, it's about getting the right result at the where it matters. Then it's supposed to take that particular spot on the main beam, and then you should be able to image that with high resolution. So this is all work that will be done by machines in coming, I would say, few years. It's coming up very fast. Machine learnings are particularly good at 2D, as I mentioned. I tried to mention. I don't know if I mentioned it when the audio was on, but machines learning is great. The whole process actually goes through a matrix learning, and since your detector is basically a 2D detector, it's very efficiently converted into Fourier or whatever machine learning algorithms you want to implement. So this is the direction we are trying to go, and it is in fact almost sure that the machines are going to be such that they will determine the resolution, they will determine all the parameters that are best for particular problem with the health or the measurement. These are just, I don't want to go into details, but these are basically a sample and an image. This is the field curvature that I was talking about. These lenses actually have, depending on the size of the lens, they actually have curvatures, which depend on the size, on the length of the mirror. You can imagine if the mirror is longer, then the curvature will be higher. If the diameter is larger, then the curvature will be kind of less. So these are all things that are going to be optimized by the machines. The machines can do this incredibly fast. If you just, for them, it's just very simple. You just try to program and they'll do this, figure out the right curvature and the right spot for the detector and give you the optimized results. What time is it? So I'm 5 minutes over. So I'm going to end the talk here. Thank you. If you have any questions, I'll be glad to take it.
Thank you, Dr. Durgesh.
Yeah.
Yeah. Any question? The session is open for discussion now. Any question from audience, please? Dr. Durgesh, what energies are involved for these neutrinos? Neutrons, I'm sorry.
So this is a good question. So ideally you want a cold neutron for most of the experiments that are done. A cold neutron means you are looking at a wavelength of about 6. It is 6 angstrom to 18 angstrom. You can calculate the energy accordingly. We generally deal with wavelengths in the neutron world. So I in my mind, I don't remember exactly how much energy it becomes. But didn't I have the spectrum? No, it was also a wavelength. So yeah. I don't recall, but the wavelength is between 4.5 to 18 angstrom. That's very typical. Okay. It depends on the source as well. I'm talking about reactor sources. On the spallation, they use between 2 to 4 angstrom. Yeah. And that is for spectroscopy. It then again changes.
And what sizes are involved in case of this coronavirus?
Yeah, that's a good question. So the sizes are, any proteins and viruses, you're looking at tens of angstrom to about a few hundred angstroms. So that is typical. So let's say under 100.
It varies, yeah?
Oh, it varies as in it's not just the viruses. The more effective solutions are thought to be in what we call the spike protein. So the mediation, the way a virus actually works is that the virus is basically useless without a host. So they always try to find a host, and the way they find a host is actually determines how dangerous or problematic it is. So it uses what we call the spike protein. That's what you can see Krur Singh's hair.
Right.
I don't know if you guys remember Krur Singh from Chandrakanta when we were kids. So it's like spikes.
Right.
And So the spikes are the more kind of, that's the target. The virus itself, because these things mutate and the approach is different, but the approach, the first papers that came way in like February, mid-February in Science was on the spike proteins. That's the target. And they are of the order of tens of nanometer.
So these method, the neutron imaging, is useful, I hope, for this coronavirus detection.
So it has limitations with imaging directly, sir, because if you imagine, these are, the resolution of imaging is of the order of few tens of microns. You can basically push to few microns if you actually optimize it, but then your field of and depth of curvature depth of view will be much smaller. So the imaging has limitation in that respect. The imaging is not going to help with directly understanding the corona. It's not going to be able to look at least neutrons. I'm sure cryo-EM will be able to say it. The way imaging will be helpful it will be able to see, for example, the consequences on the, it works like basically influenza. Okay, basically the heart is like a pump. I don't know, for physicists, I have to understand, translate things into a physics. So, for example, Raman scattering, things vibrate, right? And that's so in the same way, our heart has these layers which kind of vibrate, and that's how we breathe. And so it kind of these things go, they make these pores, and so things get more, let's say, rigid. So it can't vibrate, pulse with the same efficiency, and as a result, our oxygen intakes and they suffer, and that's how it basically acts. It's difficulty in breathing, right? So things become a little, should I say, rigid. So it can image those perspective, and I was hoping that if I have some time, I have actually done some scattering using neutron diffraction. So you can actually, with that matter, take those membranes, get the diffraction, interlayer spacings, and those things indeed do change when they're affected by, coronavirus or any influenza, things like that. There are different approaches that all come together. It's too bad. There is actually a medicine so on 15th of June, there was a news article which actually say that they're actually treating corona stage 2 or 3. When it becomes serious, that's when, the effects actually become vigorous in the lower, in the chest, and they're actually using the medications for, what is influenza? Yeah. The same medicines they use there. So it's different, stage 1 is different, stage 2 is different, 3. So it all depends on the stage. It's complicated landscape.
Yeah, that's right. So any question? If somebody has any question, please he can ask Dr. Durgesh. He is an expert in these neutron detections and neutron scattering, neutron diffraction. We are Dr. Durgesh, we are in fact thankful to you for providing us such illuminating thing about the neutron spectroscopy, and maybe this is I just wanted to correlate with the present corona epidemic everywhere, which is present everywhere.
Yeah.
So in that sense, the whole presentation was a worth presentation. So it's timely presentation for us, and we are extremely thankful. Professor Nimai, will you comment something? Professor Nimai.
Yeah, I think his you need his microphone is muted.
His microphone is muted. Yeah. Okay. Anyway, so
right.
Yeah.
Yeah.
will you comment something?
No, fine, fine. Very nice talk. It is a very innovative, very having good merit, something unique, different.
Neutron and neutrinos, they are neighbor, yeah.
but
Neutrinos and neutrons, they are neighbors, right?
yes.
The pronunciation, yes, but in actuality, they're as for apart as I can imagine. I don't know. I have a fear of neutrinos. I don't know.
No, anyway, it's very nice talk.
Thank you. So, I mean, when coming from India, I'd say we had very strong fundamentals. But when I came to States, I realized, particularly when I came to Cornell, these are very good. People have been engineers for like 3 generations, and they can open their car up all the time. So one of the things I slowly realized is that they're very good at hands-on technique, I would say. So that's something that I've been trying to learn. It's kind of a lot of art. It's, the ability to actually make the best out of what is available, which I had done previously, and then switching to actually making what you want. Okay,
That's right.
these are very two different things. Using what you have and making what you want.
Yeah. The connection is not very simple, yeah.
Yeah.
Yes. So we thank you, Dr. Durgesh Rai, and we thank you for collaborating in this conference. Yes. So I hand over the stage to the convener, Adarsh.
Okay, sir. Thank you, sir. Thank you, sir.
Who is here?
Thank you. Yes, sir. Thank you, sir.
So maybe you can give a break, or maybe you can start a new session, yeah?
Sir, I can start the new session.
Okay, thank you very much, yeah?
Thank you, sir. Thank you, sir.
So I close this session. Thank you.
Okay, sir. Okay. Thank you, Professor Chandola-ji. Now, before proceeding further, I will request all of you to kindly fill the Google form. Link is provided in the chat section of the Google meeting. Kindly fill this form by end of this session. Thank you. Now I will invite Dr. Mahipal Singh. Sir, are you here?
Yes, sir. I am available.
Yes, sir. To section the
thank you, Vaji.
And introduce our next plenary speakers. Sir, over to you.
Okay. Thank you. Thank you, Vaji. Now it's time for plenary talks of this international e-conference of recent advances in physics from to society. Thank you, Adarsh Chaudhary, Organizing Secretary, and Convener Dr. Bhuvesh Joshi ji, for conducting this session. Now, our first plenary talk is by Dr. S.G. Kaushik. I would like to introduce Dr. S.G. Kaushik. Actually, Dr. S.D. Kaushik is working in University Grant Commission, Department of Atomic Energy, CSIR Mumbai Center since last 12 years, after completing PhD from Jawaharlal Nehru University, New Delhi. His research interests are studying crystals and magnetic structure and correlating them with the physical properties like magnetism, dielectric, and specific heat of oxide-based magnetic materials and multiferroic materials to see the microscopic picture. Around 125 papers have been published in various national and international reputed journals, and he has visited several countries like United States of America, United States of Kingdom, France, Korea, for presenting the research work for experimental purpose or academic work. So I would like to Dr. S.D. Kaushik sir, please present your talk.
Thank you. Am I audible?
Yes, sir.
Okay. So thank you very much, Mahipal sir. Thank my Professor Mahipal sir, and I would like to thank the organizer for giving me this opportunity. I would like to continue with the previous talks. In the first talk, Professor Nimai Singh talked about neutrino, and then in the previous talk, Dr. Durgesh Rai talked about neutron, and I will continue on this thing. So my presentation is okay. Can you see this presentation?
Yes, yes, yes.
Okay.
Yes, sir.
So basically, I will be talking about the neutron diffraction, which is a slightly different from the previous one, but it is more like why we do the neutron diffraction for on the material which can be magnetic or maybe magnetic. So it is a basically introductory talk for neutron diffraction. Those who are not aware of this, they may get some idea about how to study the magnetism in your compound using neutron diffraction. So basically, I'll be talking about the importance of diffraction and then background of neutrons and then why we do the neutron diffraction. Then I'll give some examples so that you can have some idea that what is the benefit of neutron diffraction. And if time permits, I will be talking about some complementary facilities at our Mumbai Center, CSR Mumbai Center. So if I say take a rough example of say carbon. So carbon has a two allotrope, like one is diamond and another is graphite. So from diamond and graphite, we know these are having different properties. So like at the one point, diamond is the hardest known substance. On the other hand, graphite is very soft and easy to touch. Diamond is transparent and high reflective index, and on the other hand, graphite is black in color and opaque. On similarly, like diamond has non-conductor of heat, but graphite is conductor of heat. So like somebody may ask why, I mean, the same element having two allotrope have vast difference in the properties. So what could be the reason? So the reason lies in the structure of these compounds. So if you see the diamond, how the structure looks like. So diamond occurs in basically octahedral crystals. Each carbon atom is linked to its neighboring four carbon atom via a single covalent atom, which makes a 3D network of covalent bonds. On the other hand, if we look into the crystal structure of graphite, it occurs in hexagonal crystals. So in which carbon atoms are arranged in a flat parallel, you can see the flat parallel regular hexagons, and then these are interlayers of hexagon. So the idea is that once you know the structure of the compound, you can have more information about the properties. Once you know the information about the properties, you can have idea of symmetry of the crystal, and then what is the distance between the planes. Once you know them in and out, then you can try to modify the property for the good of it, or modifying it. Like suppose if I'm talking about the magnetic properties, so most of the compound which are I mean, if you take about the idea of say hard disk or RAM, so they have the storage media. So storage nowadays, when we are talking about, we are really require a lot of storage material over. So like the storage material is basically they store the information in the digital form, like 0 or 1. So by application of small magnetic field, we can use the 0 1 form, we can store the information like that. So once we know the physical property of our compound, so then we can modify it. So the idea is that we should be having some idea about the structure, and then if it is magnetic, then magnetic information should be known. So crystal system is everyone may be knowing that this is a basic 7 crystal systems. So cubic is high symmetry and triclinic is lower symmetry, and there are in between tetragonal and orthorhombic and hexagonal and monoclinic. So once we somebody may ask that why I should do the neutron diffraction when they can or everybody can do the X-ray diffraction using the lab X-rays. So in diffraction, that you may be aware that Bragg's law is followed. So this is a law which is followed in all the diffraction experiments, whether it be X-ray, XRD diffraction, or neutron diffraction. So why neutron diffraction? So neutron diffraction is basically it's a chargeless particle. So being a chargeless particle or having mass of the time 1.767 × 27 kilogram. So because of being chargeless particle, it can penetrate deep into your sample. So you can see if it can almost go close to your nucleus, and then it can extract more information. In case of X-ray, because of electron cloud, your X-ray cannot deep penetrate. So information which X-ray can get may not be exact or may not be specific. On the other hand, apart from that, we have a magnetic dipole. So magnetic dipoles means it's a spin half particle. So neutron carries the moment. So because of neutron carrying the moment, it can interact with your magnetic property in your sample. I will talk about it in after a few slides. Apart from that, neutron have a wavelength of typically 1 to 10 angstrom, depending upon the usage of the neutron. Like in the earlier talk, Dr. Durgesh Rai talked about that they have used a wavelength of up to 4 to 18 angstrom. So since interatomic distance is also a thought of that level, so we can study the structure. And the energy of the neutron is around typically 0.1 MeV, milli electron volt. So this is that I'm talking about the typical energy of all the neutrons, which is used for experimental purposes. So which is comparable to the atomic vibrations in the material. So you can study the dynamics also. So apart from these structure and dynamics, you can have different kinds of experiment depending upon the usage. Like in the earlier talk, Dr. Durgesh Rai talked about small angular neutron scattering. And then apart from that, we can have triple axis spectrometer, and then quasi-elastic spectrometer, in which we can study the stochastic dynamics. And then we can have the high Q diffractometer, in which we can study the glass-like material. So idea is that by using neutron, you can design your experiment or design your instrument, in fact, so for the specific purpose. Here in this particular talk, I will be mostly talking about the neutron diffraction. For diffraction, we can study the magnetic structure as well as crystal structure. But the design of the instrument is basically designed as per the usage. So for instrument which is designed for triple axis spectrometer to understand dynamics cannot be used for diffractometer. And similarly, the experiment designed for the high Q diffractometer cannot be used for any diffraction experiment or sense experiment. So the instrument design is usage specific. The starting of this neutron diffraction or dynamics started long back. I mean, Professor Scholl studied about the structure using neutrons way back in 1946, and then Professor Brockhaus studied the dynamics of the sample. So the structure study and dynamics study depends upon the elastic scattering or inelastic scattering. In case of study of dynamics, it has to have inelastic scattering, and it means there is a loss of energy. The incoming neutron falls on your sample, and then it goes away from your sample, and then there is a loss of energy. And by studying the loss of energy, you can model about your dynamic structure factor and study the dynamics in your sample. And in case of elastic scattering, when neutron falls on your sample and then goes away without the loss of energy, you can study the structure. So then these two gentlemen got the Nobel Prize for this properties in 1994. I mean, it was quite delayed. And one more idea about the neutron is that if you study about X-ray diffraction, so X-ray, the intensity is intensity of X-ray diffraction depends upon the monotonous. It depends upon the Z. So as your Z increases, your intensity of the X-ray increases like this linearly. But in case of neutron, there is no Z dependent. The intensity is scattering length dependent. Scattering length for particular atom. So you can see the scattering length of particular atom is not it's not following any particular path, or it's not following any. It's independent to any other thing. So the benefit of that, you can if your sample is having closer by elements like iron and nickel. So iron and nickel, since having different scattering lengths, you can identify these iron and nickel in your sample conclusively as compared to X-ray, because in X-ray you may not be having clear-cut indication of iron and nickel because they are very nearby and cannot be distinguished carefully. So that is one benefit. And another benefit is that the atomic form factor for X-ray falls as a function of theta. As a function of theta, suppose if you see any X-ray diffraction pattern, you will see that at higher angle, the intensity of these peaks will start decreasing. But in case of, because of this decrease in the intensity, when you model your sample, analyze your data, you will not get true information because of your intensity is falling. But in case of neutron, this is atomic form factor is constant. So because of atomic form factor is constant, you can see the intensity of the neutron deflection pattern does not fall as a function of theta. I'll show some example in which you can see further. So as I was talking about that, in case of X-ray, you can see the atoms like this. Suppose lightest element is hydrogen, so you can see a small dot. And as you go with the higher Z, you will see the elements like this. But in case of neutron, you can see element depending upon their scattering length. So because this is a scattering line dependent, intensity is a scattering line dependent. So you can clearly identify what are nearby element also in your sample. So I was talking about the magnetic moment of the neutron. So magnetic moment means neutron is carrying the spin half. So because of spin half, it has a definite magnetic dipole moment. And when it interacts with your sample, which is if in magnetic state, it can interact with the magnetic state of your sample and can give information about the magnetic property of your sample. So one may ask that what is the benefit of it? Because magnetization you can study by other means like maybe physical property measurement system. These are the system which can study the magnetization as a function of temperature or magnetization as a function of field at constant temperature. So benefit of MPPMS like instrument is that you can study the how much magnetization is there in your sample, but you may not be able to understand how the spin structure looks like. Suppose you have a transition temperature, say 75 or 80 Kelvin. So below 80, you will be able to understand what is the magnetization in your sample, but you may not be aware that how the spin structure looks like. If you are not aware of the spin structure, if you try to modify the property, you will not be able to see. So that is the idea. That is the more benefit of studying the magnetic structure using the neutron diffraction. Definitely in neutron diffraction, the magnetic part has a form factor dependence. So you can see it falls as a function of theta, but still when you see the magnetic peak, you can still model your sample and get the idea about the magnetic structure. So this is very first example which was studied using neutron diffraction. So if you can see, this is MNO neutron diffraction pattern. MNO neutron diffraction pattern studied at 293 Kelvin. So you can see these are the these are the structural peak. As you go down to say 80 Kelvin, and you can see there are few peaks which are coming up. And this particular peak is quite intense peak. So this peak is basically magnetic peak in your sample. So when you analyze your sample or model your sample, so you can determine the magnetic structure, how it looks like. So in case of MNO, your Mn is the magnetic atom. So the spin are arranged in the antiferromagnetic feature like this. This is like antiferromagnetic situation. So this was very first experiment carried out in early 50s. So at that time, instrumentation was not that much advanced, but still the idea was there that you can study the magnetism using the neutron diffraction. So now within the magnetism, there are different kinds of magnetism like ferromagnetic or antiferromagnetic or ferrimagnetic. So in case of studying the magnetism, you can see there are ferromagnetic or antiferromagnetic, but within antiferromagnetic sample, you can have different kind of antiferromagnetism. Like this is one example which shows this is CE type, means within the layer you have antiferromagnetic properties, and in A type you can see interlayer antiferromagnetic property, but within the layer they are ferromagnetic. And this is C type, in which you see layer-wise antiferromagnetic property. So if you see carefully, depending upon the type of antiferromagnetism, you can see different kind of peak which are coming up. So this is the idea of, benefit of neutron diffraction. Just by looking into the pattern, you can have, and modeling the your diffraction pattern, you can see what kind of magnetism is there, which you cannot study using the magnetization measurement very easily. So basically the idea of, or maybe you can say the difference between X-ray and neutron is that in X-ray you can see the bone structure, means you can see how the atoms are arranged in your in your compound, how the atomic positions are there. But in case of neutron, you can still see how the magnetic atoms are arranged and how the spins looks like. So that is the more benefit of neutron diffraction. The sources of neutron, as definitely there are two sources as talked about by Dr. Durgesh Rai in the previous talk. One is research reactor and another is spallation source. In research reactor, we have controlled chain reactions through which the unused neutrons are thrown out in the form of neutron beam, and then from neutron beam we can choose about the neutron of particular wavelength. And in case of spallation source, you have a very high Z element in which is targeted by say proton, then it can emit the neutrons. So this is spallation source. You can say it's a safe source of getting neutrons because there is no control chain reaction involved. But definitely, it most of the time it doesn't give you the continuous source of neutron. It's basically pulse-based source. So you get pulse of neutrons, and you can do experiment definitely. In India, we have one neutron diffraction facility or neutron source. This is Dhruva in BARC. So earlier there were Cyrus also active, but now Cyrus is decommissioned. Only Dhruva is working. You can see the layout of this is basically the reactor hall in which you can see different experiments setups are there. So this is our setup, diffractometer. This is called PD3 powder diffractometer 3 beam line. So you can see the layout like this. So every beam hole, like neutrons are coming from these beam holes, and you can see different instruments are there. So neutrons, these different instruments are corresponding to the uses, like this is triple axis instrument and this is polarization, and then this is single crystal diffractometer. So depending upon the uses, the people in BRC have designed the instrument, and these are basically guide tube. So guide tube is nothing but basically when you have the neutron beams, then if you want to have high wavelength, means you want to do small angle neutron scattering, you need to see in very low Q rate, very low Q range or very low theta range. So for low Q, Q is nothing but 4 pi sin theta over lambda, means you need to have less energetic neutrons, means cold neutrons. So one option of cold neutron is that you pass the neutrons through some liquid helium or some medium so that it can lose the energy. Other option is that you allow the neutrons to pass through a long distance, and then in this process they will lose energy and you can get the less energetic neutrons, and then you can have high wavelength neutrons. So you can, in BRC we have two science experiments and then reflectivity also. One is a neutron reflectometer. So I'm coming to our diffractometer beamline. So we have a beamline which is throughput beamline. So we have a typical beam size of 15 to 25 millimeters square, and flux at sample is around 7 to 10 power 7 neutron per centimeter square per second. This is not very high flux, but medium range flux detector. So we can do most of the experiment which you can do in any other neutron scattering center or neutron diffraction center. So neutrons are coming from the reactor, and then these are the beam hole through which you can see the beam of neutron coming like this, and you have sample, and then we have a detectors over there. So these are position sensitive detectors. Position sensitive detector means detectors are static, not moving, unlike in X-ray. So then we have diffracted beam coming from the sample, and then we can get the pattern. And on the beamline, we have option of carrying out the experiment, temperature dependent experiment from say 2 Kelvin to 300 Kelvin. And in this situation, we have option of field also. So we have two instruments for that. So one instrument is simple CCR. This is cryogen free closed cycle refrigerator. So we can carry out a neutron diffraction experiment from say 2 Kelvin to 300 Kelvin. And similarly, we have another system which is 7 Tesla magnet. We can go down from go down up to 1.6 Kelvin and up to 300 Kelvin, but we can apply the field up to 7 Tesla. And this is some recent visit of PM in our diffractometer. And this is the typical uh, uh, diffraction pattern, which similarly looks like more like X-ray diffraction, but definitely you can get more information if you are doing the neutron diffraction. So you can see these red dots are observed values, observed intensities, and blacks are calculated intensities. If you, some of you are familiar about the analysis of the data, this is basically analyzed using the foolproof method, in which we give a model of our sample, and based on the modeling, we need to know what are the possible Wyckoff position or atomic position element possible. I mean, the element in your sample. So for those elements, you should be knowing about the Wyckoff position, and then rough idea of the cell parameter, and then space group. So if you have these few information, then you can analyze the data. You can start with an input model. Once you have input model, then you can further analyze it, and try to calculate the calculated intensity similar to the observed intensity. So if you get the difference like this, so it means you are able to model the your compound very perfectly, and then you can assume that this is your perfect model for that particular sample. So as I talked about in previously, that we have option of different wavelength. So this experiment is carried out at 1.48 angstrom, but we have option of changing the wavelength. Suppose you have a high Q, you have high larger cell. Larger cell means you have large ABC parameter. Then in that case, your magnetic peak may not come at that particular angular range which we have. So we can go to higher wavelength, and then we can try to catch the magnetic peaks in the low angle region. And these are basically your sample cans. So we put the sample in, these are vanadium cans basically. Why we use vanadium? Basically because vanadium is an incoherent scatter of your sample of neutrons. So the peak coming because of basically the scattered neutron from the vanadium will go into the background. It will not form a peak. So whatever data is coming will be because of your sample only. There will be no peak because of vanadium. So that's why we use a vanadium can. So the diameter of the vanadium can is around typical 5 millimeter, and the length is around 50 millimeters. So as mentioned, as shown in the previous slide, we have a beam size of say 25 millimeters, so that you can totally expose your sample to the neutron beam, and then you can get some pattern. So I'll be coming to the few experiment which we have carried out in the recent past on our diffractometer. I think how much time I have? Hello? Can you listen me? Hello?
Yes, we can listen to you.
Okay. So, okay. How much time I have? So, okay, so I'll be talking about some example which we have carried out on our diffractometer. So this is one example in which we have tried to study. This is Langasite type of compounds, which is supposed to be multiferroic in nature. So we have tried to study the magnetic structure of these compounds. So as I mentioned that we should be knowing about the space group of your sample, and possible atomic position in your sample. So we have carried out the neutron diffraction like this for this compound. So as I was talking about, you have atoms and possible Wyckoff position and their XYZ coordinates, and then cell parameters. So once you have this information, then giving this information in the input file, you can try to fit your sample data, and then you can see this black dots are basically observed data, and red lines are calculated lines. So the difference between them is more or less very much linear kind of thing. So reasonably good fitting. And fitting parameter, you can also see this is basically I'm using full proof for analysis of the data. So you can see what are the chi-square value and r theta, rp, and r parameters. So these are well within the range of goodness of fitting parameter. So the idea is that this is the pattern taken at room temperature, and when we are doing the neutron diffraction, we cannot do the neutron diffraction just like that, because as I mentioned, we have only one source of carrying out the neutron diffraction. So in that case, since there's only one facility at in our India, so there's a long queue for that. Yeah. Hello. Hello. Hello.
Please.
Yeah. Please tell me.
Conclude your talk, sir.
Okay.
Can you hear me?
Okay.
Please conclude, sir.
Okay. 5 minutes.
Thank you, sir.
Okay. So basically.
Yes, sir. 5 minutes, sir.
So we should have idea about magnetic transition temperature. So for this particular temperature, we have around 26 Kelvin. So we can study the neutron diffraction at low temperature. So for this particular temperature, we have seen the neutron. This is basically 300 Kelvin, and this is 3 Kelvin. So if we see at 300 Kelvin, we have 3 peaks, but at 3K we have our one new peak which is coming up. So it is a clear signature of anti-ferromagnetic field, because of up and down spins, you have cell doubling or cell tripling depending upon your sample. So because of that, you will get new peak. So by analyzing this data, we can see how the spin structure looks like. I have shown you like along the c-axis. So this is basically spiral kind of spin structure. So since time is less, so I will just quickly go to some more examples, and then we can conclude and we can have some questions. So this is another study which we have carried out, in which we have this is the SRMNO3 sample, in which we have forced fluorine to go at oxygen site, but how to identify that oxygen has gone, this fluorine has gone to oxygen or not. So we have carried out a neutron diffraction at room temperature. We can clearly see the difference, that there is some difference coming up at low angle. So by analyzing this, we could identify that fluorine can go to the oxygen. See, this oxygen being a low Z element cannot be definitely studied by X-ray diffraction, but in case of neutron diffraction, as this is scattering length dependent, so oxygen can be studied on using neutron diffraction more conclusively. And then one more example, which is and double perovskite, for which there was no report of spin structure. So we have carried out neutron diffraction for this compound, and we can clearly see how the magnetic structure, which is antiferromagnetic, looks like. And some more example, like this is another example, Bi2F409, in which we could see there was an indication of short range ordering at room temperature. But when we carried out the low temperature neutron diffraction, we could see the short range ordering is converting into the long range ordering. So to understand whether the short range ordering is magnetic or non-magnetic in nature, we have carried out the this polarized neutron diffraction. Polarized neutron diffraction at low temperature we have carried out, which is carried out at different instrument, not on this instrument. So we can see that this short range ordering at room temperature is magnetic in nature. And similarly, there are other samples which we have done. So for this more sample, this cobalt 4 TB209, the magnetic structure we have reported. So and a few more samples, like this is calcium doped LaOPO3, in which it has been used for sulfur oxide gas sensing. So we could not see if we are using it for gas sensing. We need to know what is the exact position of oxygen. So using neutron diffraction, we could see what is the, upon the calcium doping, there was a change in the oxygen, there was oxygen deficient. So instead of LaFeO3, oxygen became 2.95. So oxygen became 2.95, so it can be used for gas sensing applications. Like these are the gas sensing application carried out at different instruments. One more thing is that using the neutron diffraction, you can identify if you have Fick's coexistence or not. This particular compound, this is LaSiMNO3 in nanowire form. So upon low temperature neutron diffraction, low temperature magnetization, you can see because of for nanowire and the bulk, there was a definite difference between the magnetization, but we could not identify what could be the reason for that. But upon carrying out the neutron diffraction, we could identify that there was a phase coexistence below 200 Kelvin. So at below 200 Kelvin, there was a two phase. One is antiferromagnetic phase, another was ferromagnetic phase. So, I mean, idea is that by using the neutron diffraction, there are n number of things in the magnetism itself you can try to understand. I'll show you one or two more example. After that, we can conclude. This is YMNO3 sample, which is multiferric in nature. So you can see at 10 Kelvin and 300 Kelvin. At 10 Kelvin, you see the magnetic peaks are coming up over there. At 300 Kelvin, there is no magnetic. And upon doping iron at Mn site, say 0.5%, 5% or 10% doping, you can see in these slides. So for pure MnO3, we can see the magnetic structure coming, magnetic peaks are coming over here. And upon doping the iron, you can see the magnetic peaks are changing their place. So changing their place, you can see in this figure. So this is pure MnO3. And 5% doping and 10% doping, it shows so that is the idea that if you carry out the magnetization, you can see for these things, the magnetization Pn is more or less similar, 71 Kelvin, 71 Kelvin, 70 Kelvin. But you cannot identify what is the magnetic structure looks like. By carrying out the neutron diffraction, you can see that there is a change in the magnetic structure. The structure is changing, and then this can be identified using this neutron. And I'll quickly take one more example for field effect, magnetic field effect I can show you. So this is calcium-3 cobalt manganese oxide. We have carried out neutron diffraction. This is another multiferrite sample. So at 1.48 angstrom wavelength, we have carried out a diffraction. It shows the antiferromagnetic behavior. So the spin structure looks like this. Okay, but when we apply the 5 Tesla magnetic field, we can see this is in 0 field and this is in 5 Tesla. So these are Mn spin and cobalt spin. So upon the application of field, we can see the spin of cobalt is flipping along the Mn field, along the Mn direction. So by application of field, we were able to flip the magnetic spin of cobalt. So I mean, idea is that the application of magnetic field under I mean neutron diffraction study, we can see whether if your field is strong enough and playing some role in the changing in the structure, you can also understand that very carefully. So if time permit, I can show you a few more examples. Otherwise, we can finish here. Mahipal sir? Hello? Hello?
Kaushik sir?
Yeah, if time is there, then I can continue. Otherwise, we can.
Sir,
okay.
No, sir. Now, sir, please, sir.
Okay, so we can take some questions now.
So can I ask a question, please?
Yeah, sure.
So can you tell me some details of the characteristics of Dhruv reactor? I'm just curious.
Okay, but this is basically uranium-based reactor. So we have a continuous neutron beam, and it has almost 15 neutron beam holes. So all the 15 or 14 neutron beam holes have different kind of experiment. Like we have 2 sense experiments. Those are at room temperature only, not at low temperature. And out of these 2 sense, there is option of having less than 30 nanometer and more than 30 nanometer. This is basically ultra sense and normal sense. And then we have a reflectivity, neutron reflectivity, and then we have 3 diffractometer. 3 diffractometer, 1 diffractometer is ours, which is having option of 7 Tesla magnetic field and low temperature. Other 2 diffractometers have normal low temperature. And then we have one single crystal diffractometer, and this one is small triple axis instrument is also there, and one high Q diffractometer is also there. So if you want some detail, I can mail you. I think you are the Dugesh.
Yes.
Yeah,
That
yeah.
will be
So we
great.
can, yeah.
Did
So I
you
can,
know what's the energy range that is, like, you basically it's a reactor, so I'm guessing you have some kind of a
okay. So this
you
is
know,
basically
into the center of the reactor you actually place your I don't know what to call, but we used to call it handle, depending on what kind of neutrons you want, right? So I'm just curious about the spectrum of the neutrons that you
okay.
get.
So basically, we have a neutron energy range up to 10 milli electron volt. So 10 milli electron volt. So then you can choose we have a basically select. You can choose your wavelength by placing the. Uh, uh, we have a silicon a single crystal kind of uh, uh, collimator. So by using the collimator, you can choose certain wavelength of neutron. So option of wavelength is up for diffractometer. We have for our diffractometer we have 4 option of wavelength, and for other diffractometer they are mostly up to 1.2. For high Q they have I think up to 4 angstrom or 4.5 angstrom. So for science, we have a higher wavelength. We have guide tube lab, which is typically, I think, 10 or 15 meter long. I'm not sure, very much sure, but we can do the experiments.
Nice. Thank you.
Okay.
Okay, thank you, sir. This was
Okay.
very informative and beautiful talk by Dr. H.D. Kaushik, and he explained the importance of diffraction and explaining the basics of Black's law. He explained the basics of neutron, why neutrons are necessary for diffraction, and Dr. Kaushik has explained low energy neutrons and the importance and usefulness of low energy neutrons, and magnetic scattering, and the national facility for neutron beam research, and how to use the diffraction technique for various purposes of society. Thank you, Kaushik sir. Your talk is
Thank you.
very nice and informative. Thank you, sir.
Thank you. Thank you.
Now our is dynamics on networks. Dr. Isplatus at Parvesing. Dr.
Yes,
Parvesing.
hello. Sorry, my microphone was muted.
Yes, sir.
Also, the audio is a little broken.
Introduce Dr.
Can everyone hear me?
Dr. Parvesing of Muradabad affiliated to
Pramesh, I was able to hear, at least from my side, pretty well.
Okay.
But Dr. Mahipal sir's volume has been cutting, as you rightly
Yes.
So it seems like you are on the go.
Oh, yeah. Wait, Adarsh is
now he postdoc at Northwestern University. After the move to University of Houston, where he is working in the physics department postdoctorate fellow. His research focus, he is interested in applying network models to study complex like biological, social. Now I invite Dr. Pramesh Singh to talk.
Okay. Well, first of all, thank you for.
Please unmute your. Now.
Yeah, so I think I'm ready to go. Well, first of all, I would like to thank the organizers for giving this opportunity to speak to you people, and it's really good. I've listened to 2 talks so far, and I apologize for being a little late. Okay, so it's also my first time using this, so I am learning. Okay, Okay, you are presenting your screen, and oh, I'm also going to turn my camera off, so maybe it will be clearer. Can you see my screen?
Yes.
Okay, good. So full screen. Okay, so I'm going to start with a confession that I'm going to try to interpret Vicky Weisskopf in what he described as two frontiers of science, namely the internal frontier and the external frontier. Here's a picture of Vicky Weisskopf. I believe he was a professor in physics at MIT. He's from Austria. And so what are these two frontiers? I've made my own list of pictures that sort of describe the idea. The external frontier is about exploring new laws of nature, or what is beyond our current understanding, going where no one has gone before. In other words, pushing the envelope. So problems like what's dark matter, or elementary particle physics, string theory, cosmology, these kinds of questions, or fundamental questions in these areas, would fall into the category of external frontier. Whereas this other frontier that Weisskopf called the internal frontier is a much broader frontier. So where the external frontier concerns natural phenomena whose fundamental governing laws and principles we do not understand, and we're trying to discover them. In contrast, the internal frontier is it concerns with problems where the basic principles are known. Well, of course, we can never be certain that we know everything, but at least there's a belief that all the physics, or all the fundamentals of the interaction mechanisms and everything is known, yet we do not understand these systems because they're very complex. Or so because of the complexity of the phenomena, it's very difficult to understand these systems. So an example of a question that an external frontier concern, like what is everything made of? So you build these colliders and you try to break things into smaller and smaller components until you find out the next layer. But a much harder question is how is everything put together? So what are the relationships? How do you
Ramesh, sorry to interrupt. It seems we kind of lost you. Is that right? Oh, maybe not. You're fine.
Oh, okay. Oh, I was worried too. Okay, thank you. So how to put these elementary components together is a much harder question. You may agree with me, you may disagree with me, but that's the whole point of this discussion. A very interesting question is often asked is, can we build a machine that can turn grass into milk? Is that physically possible? As a matter of fact, these machines exist. And one of the pictures here shows such a machine. This is a cow. It can feed it grass, and it can turn the grass into milk. How does it do that? No idea. And even though these machines exist, like, we have no idea how they function. So that's the internal frontier. Okay, so moving on, complex systems. So my talk is going to be about complex systems, and I also have to say that there is no formal definition of what a complex system is, but oftentimes there are a few general characteristics that we attribute to complex systems. For example, they are composed of many interacting components, a large number of interacting components. They often exhibit emergent properties or patterns that that arise purely from local interactions, and there's no centralized control in the system, and yet the system is able to achieve or display these beautiful emergent patterns. As you can see on the picture to the right, it's a swarm of birds. It's a classic example that people use when they describe a complex system. And I'm sure all of us have seen these swarms. There is no central leader bird in these swarms. And so what the birds do is they just follow their surroundings. So the interactions are purely local, and yet they don't bump into each other. There's no, they don't display complicated random motion where they might hit it. Somehow they're able to function as a unit, as a whole. And perhaps if you're looking for a definition of complex systems in less than 4 words, Philip Anderson said it the best: more is different. When you have fewer interacting entities, things are simpler, but as you add more interactions and more things to the system, it becomes complex. So the next question is, why should a physicist care about these things? Well, it turns out that these systems display phenomena like universality and scaling and phase transitions and other critical phenomena. And physicists over the years have already developed tools. So there are already existing tools in their toolboxes that they have used for a long time to study physical systems, and the same techniques or same approaches could be useful in describing these systems. Okay, so moving on to the next slide. What is a network? So in a very basic, simple terms, a network is a collection of nodes with links between them. I am sort of presenting it in a way that's a very new field, but that is actually not the case. The story of networks goes as far back as the 18th century with this problem of 7 bridges of Königsberg. So in the city of Königsberg, so the city is set on both the 2 sides of a river that cuts the city in between. And there are two big islands in the city. So the problem of 7 bridges was to construct a walk through the city that you travel the whole city by crossing each bridge exactly once. And you can start from anywhere in the city, but the goal is to go to every island or every part of the city, but the only thing is you could only cross every bridge once. And the solution was given by Leonhard Euler, the famous mathematician, and he actually showed that there is no such path, and such a walk would not be possible. How did he do that? He simplified this problem to a network. So the network is an abstraction of the problem, and where you don't care so much about details. You don't care about how big these islands are. You don't care about what these bridges are made of, or whether or not there is water in the river. So you skip a lot of details that are irrelevant to the problem, and so you're basically reducing the problem to its essential components. And by doing that, Euler was able to show that this problem could be mapped onto this network shown shown in blue by blue nodes, and the I believe the edges would represent the seven bridges. So, and that analysis gave birth to the field of what mathematicians call graph theory. We call it network science, or honestly, I don't know if there is a difference. Maybe there is, but for the purpose of this talk, I'm just going to say that this is just a terminology. Okay. So there are many other ways to study complex systems. So why networks? So I would argue that networks provide a way to think about a wide range of systems. So in some sense, it's a generalized framework or abstraction where you could think about different types of systems, and yet you can use the same formalism to describe, to understand, and to predict these systems. And so one of the nice things is that the techniques that we will develop, or we are developing, or we have developed in networks, graph theory, it can be used to understand systems that are very different from each other. Here I have shown a few pictures. The first one is I think it's the internet network where routers are connected to each other by physical links. Second is a protein-protein interaction. So each node is a protein, and there is a link if the two proteins interact with each other. Third picture is a social network where links denote friendships between nodes, which are people. And the picture on your bottom left is a network of natural gas pipelines in Europe. So this is more like a physical infrastructure network. The bottom right is a network of flights. So it's an airline network where it represents a transportation network. So even though these networks, these systems are very different from one another, as you can see, we can use the same kind of techniques to understand them. And also, like these systems generate a lot of network data, and we're familiar with some examples in communication, like social networks, or in biology and biomedical systems. You have lots of biological and biomedical data, which often happens to be in form of networks. And of course, there's a lot of data on human behavior. So this tremendous amount of data has to be analyzed to understand these systems, and I think networks offer a good framework to study them. Okay, so how do we represent these networks? On the last slide, I showed you these beautiful pictures, and that is one way to represent a network structure by visualizing it. Here I've shown a very, very simple network of 5 nodes with connections between them. It doesn't really mean anything. It's just an abstract network. So visualization is one way, but there's a more useful or more a better way to represent this network structure. It is by using what is known as an adjacency matrix. So for the same example network that you're looking at, the adjacency matrix looks like this matrix with zeros and ones. What does it mean? So I have basically ordered each one of nodes. So it's a number. So they're ordered by 1 through 5. Basically, order is not really important. What's important is that if you arrange your nodes in a particular fashion, what the adjacency matrix or an element in the adjacency matrix tells you is that if if the ith row and the jth column of the matrix is 1, that means nodes I and j are connected. And if it's a 0, that means there is no connection between those two nodes. So these two representations are equivalent. And as you also notice that the matrix here is symmetric, which represents an undirected network. The networks in general could be directed, where the matrix will not be symmetric. You can also have a weighted network. So here, this network is binary. Either you have a link or you don't have a link. You can also consider or think about situations where these links are weighted somehow, depending upon the system. In that case, those elements in the matrix would be the link weights. As you can also notice that the diagonal of the matrix is 0, which means the node is not connected to itself, although in some situations that may not be. So this is not the most general form, but it's probably one of the most simplest examples I could think of. There's also another kind of network you can imagine where these links have a sign associated to them. So links are either positive or negative. And that's something I will be touching upon later, the later part of my talk. So either visualization or matrix, it's perfectly equivalent. It's the same network, but you can represent it any way you like. Matrices are easier to deal with mathematically, although it may not always be a good idea to represent your network with this matrix. Imagine a network that has a large number of nodes, and the network is sparse in the sense that you don't have a lot of links. So storing this matrix, if you have millions of nodes, then you have a matrix of million by million, and a lot of these entries are 0. So it's not very useful to store your network in this form. Perhaps a better way is to list these links. So you would have a list of 2 numbers, 1, 2, 1, 3, 3, 4, 3, 5, 2, 4, something like that. And then you get rid of all the zeros. And that's also fine. Okay, so one of the earliest models of networks was proposed by these Hungarian mathematicians, Paul Erdős and Alfred Renyi, who proposed this Erdős-Renyi model in the late 50s. Oh, by the way, Paul Erdős is the same mathematician who's known for Erdős number. So what is, yes?
Ramesh, sorry for interruption. Can you do it? Means, please stop your presentation and then restart to share your screen, because we are not able to watch your screen.
Oh, I did not realize. Okay, let me do that.
At least from my side, I was able to see. So
okay.
It doesn't matter. Probably it's always a good idea.
So what should I do? Should I continue or does anyone else?
No, you should continue.
Oh, okay.
No, you can continue, but again share your screen.
Oh, okay. So I will. Okay, so I'll hit stop sharing screen, and then I'm going to. Okay. Let's see if this works.
Ramesh looks good.
Okay, good, great. So this network model it's called a random network, sometimes an Erdős-Renyi random network, and various other names. But the model itself is very simple. So you start with n nodes, and okay, so the network is going to contain n nodes and m links. Suppose you have n nodes and you have m links to distribute. You can construct a probability parameter p that will depend on, that's related to the total number of links in the network. And so you can also describe the network in terms of the number of nodes and the connection probability p. And what this model does is it simply picks up every pair of nodes and throws a connection with the probability p. So with probability p, which is independently chosen for every pair of nodes. So every link is independent from every other link. And so with probability p, you connect the two links, to the two nodes. So with this simple model, you can construct a network, although the model itself, it does not describe one particular network, but it's used to describe an ensemble of all networks that are possible. So you're looking at this ensemble of networks and not just one, but that's the model. But if you follow this construction, then you can derive the degree distribution for this network, and the degree of by degree I mean how many connections does a node have. So in this case, k is the degree of a node, and so when I say a degree distribution, what I'm asking is, well, what is the probability that a randomly chosen node has k connections? And that probability is given by this binomial distribution. And it turns out that if n is large, n times p is a constant, and in that large n limit, this probability distribution takes the form of a Poisson distribution. Okay, so this model allows you to understand network structures probabilistically. So you can derive sort of an expectation for various properties of the network. So you could ask, well, what's a typical degree of a node? What's the path length between two nodes in the network? Or how clustered is this network? So in a way, this works as a null model, where if you have a real world observation on a network, it answers the question of how surprised should you be if you see a particular network structure, where you assume that networks are formed by this model. Okay, so of course, it turns out that it's nice. You can do beautiful math with this model, and there's a huge literature devoted to Erdős-Rényi networks, but it turns out that it's not really a good description of real-world networks. So what do I mean by that? So real-world networks are very different, and they're often not described by a bell-shaped curve. So a bell-shaped curve looks something like this, where you have, let's say, if I'm looking at the degree distribution, for example, and a bell-shaped curve here shows you there is a characteristic degree that every node has roughly same number of degrees. That's what you get from the Erdős-Rényi model, something like that. There is a characteristic number of connections that you can that you're going to observe. But it turns out when people looked at empirical networks and plotted the degree distributions, it was not a bell-shaped curve. What they found was that that most of these networks have a power law degree distribution, and in fact, many real-world networks are believed to have a power law degree distribution, even though that claim is disputed. But nonetheless, they're far from being described by a bell-shaped curve or a Poisson distribution. And that is precisely the reason why on an average your friends are going to have more friends than you. So it's a direct consequence of the power law, the scale-free nature of the network. So in a scale-free network, you have the degree distribution given by power law, which looks something like this. So you have a probability of having k connections, and that goes as a power law. So a defining characteristic of these power law networks is that you have lots of nodes with very small, very few links somewhere in this region. And you also have few nodes that have very, very high number of connections. And so these networks contain hubs. And a generative model was proposed in the late 90s by Barabashi and Albert, where they present this model that generates a power law degree distribution. The way it does is it follows the principle of preferential attachment, where instead of randomly connecting pairs of nodes, you bring in a node to the network that you start with some initial network with a few initial nodes, and it's also a growth model. So the network is also growing. So you're adding new nodes to the network, and the idea is that you add a link. So a new node comes into the network and it attaches to a node I, which is already in the network, with probability that's proportional to the degree of node I. And over the years, there have been many other network models that capture a number of other features for the for networks, and some notable examples are, for example, you have a small world network, and this tells you that there is a very short path that connects two random nodes in the network. And I don't know if any of you is familiar with the 6 degrees of separation, or the Milgram's experiment, where they found that the world is really extraordinarily well connected, where you can reach anyone in the world with 6 hops. There are models called random geometric graph models, which where the nodes could have some physical location, so that there is some spatial distribution of these nodes, and so on. So there are various other models, and I'm not going to go into the details, but just to give you an idea that these models are there and that they're useful. Okay, so I'll be shifting gears now. So far, I've only talked about a structure of networks, and understanding the structure of networks is useful. But the ultimate goal is to describe the dynamics or the function of the system. After all, we're interested in the behavior of these systems. So the question is, how does structure relate to function or dynamics, or vice versa?
Dr. Parmesh Singh?
Yes.
Sir, please, now you may conclude.
Oh, already? Did I?
Okay.
Oh.
Thank you, sir. Please conclude, sir.
Did I spend? I thought I just started. Okay. All right. So, okay, I'll quickly.
Yes, sir.
Do in like 5 minutes or a couple more minutes. So, okay, I'll do it quickly. So, okay, I'm going to skip this and move to social systems. And so a social system is is characterized by these interaction mechanisms that are not physical. So in physics, we know the constituents of a system, and we also know how they interact precisely. But in social systems, interactions and who interacts with who are often not known, and there are interaction mechanisms that people have described in social systems. For this talk, my plan was to give you a flavor of this particular interaction mechanism called structural balance. And what is structural balance? I'm going to, okay. So the basic idea of structural balance is that your friend of my friend is my friend. A friend of my enemy is my enemy. An enemy of my friend is my enemy. An enemy of my enemy is my friend. So if you impose those conditions on a network, what you get is that networks would have friendly and unfriendly connections. So you can have the dashed line connections, which are negative, and the solid lines, which are positive connections. And it turns out that balanced triangles would contain an even number of negative links. So that's the idea. This is an example that I'm going to skip, and moving on to the model that I was going to talk about. So in this model, I have a population of three entities. You have, you can call them leftists, centrists, and rightists. So each node can be in one of these three possible states. And a connection between different types of these nodes could be positive or negative. In fact, for this model, all connections are positive except when there is a connection between a leftist and a rightist, because they're too far in their opinion space. And consequently, there's only one type of triangle in the network that's going to be unbalanced, which connects the leftist, rightist, and centrist. So any triangle that has all three nodes in the network, L, R, and C, is going to be unbalanced. And okay, I'm going to skip this and just move on to the definition of the model. So this model starts with a population of few leftists, rightists, and centrists. And with probability P, I'm going to randomly select a node and convert it to a centrist if it's already not a centrist. So this is like some kind of an external influence. You could think of a media or campaign or something. And with the probability 1 minus P, I'm going to pick a triangle and check if it's balanced or not. If it's balanced, no problem. If it's unbalanced, I'm going to balance it by changing the state of one of the nodes. Okay, I may not have time to describe exactly what the rule is, but nonetheless, there's a rule by which you can select and convert one of these nodes. You can write down the mean field equations where X, Y, and Z are the densities of leftists, rightists, and centrists in the population, and how they evolve. It turns out you only need 2 because X plus Y plus Z has to be 1 if you have a population of N. So if you know who the leftists and rightists are, you already know how many centrists you have. It turns out if you do this mean field analysis, you find that in addition to all centrist consensus state, which is absorbing, that means if you start with centrist population, there's no evolution, the system is stuck there. You also observe 2 more states or 2 more fixed points, depending upon this range of parameters and the strength of your external field. And this is a phase diagram that shows the evolution of the system. So depending upon where the system starts, so any point in the system tells you what's X and what's Y, and that is enough to describe the whole system. So in the strong field case, where your P or the external influence is greater than some critical value, which I showed here. So the system has a critical point in terms of this external influence field. If this parameter P is greater than this number, you only have one absorbing state, and it doesn't matter where you start in the system, you'll always go to this absorbing or the equilibrium state where everybody is a centrist, and it happens very quickly. However, if your field is not strong enough, that means if your P parameter is less than a critical value, which in this case, for this range of parameters, it's 0.27, and the example I'm showing is for a choice of P that's less than the critical point, you you observe that two more fixed points emerge, the metastable fixed point and the saddle point. The idea of the metastable, so the saddle point is unstable. So if you start in the vicinity of the saddle point, you're quickly going to leave that point. Absorbing state still is there, but it might not be very easy to reach there because now your field is not strong enough. The metastable state is a stable state only in the thermodynamic limit. So if you have, if your system size is infinite, yes, that state is going to be stable. But for finite systems, that's not the case. And this is what I've shown here through some simulations on a small 100-node network with alpha. I didn't describe what the alpha is, so figure out alpha is some range of parameters. So in the weak field case, you have the system just goes around the metastable point forever without leaving the vicinity of the point. But if your field is strong enough, it doesn't matter where you start from, you're quickly going to get sucked into the absorbing state. Okay, I will skip this, and with that I will summarize. So I hope I've convinced you that networks are tools that you could use to model complex systems, and it's a very useful framework. I talked about topology and dynamics of networks, and in particular, I spoke about social balance in social networks by presenting this three-state model, which couples the dynamics of social balance with external influence. And with that, I would acknowledge funding from these agencies. And here is my contact information. If you have any questions, even after the talk, feel free to reach out. And with that, I will stop here and we'll be happy to answer if you have any questions.
Now this talk is open for discussion. Any query, any question, you can talk. Is there any question? Nimai sir, would you like to comment on this talk? This talk is very interesting and the latest. Nimai sir.
Nimai sir, you need to
unmute
yourself.
Microphone is muted.
Nimai sir, your microphone is muted. Please unmute. Nimai sir, please unmute.
Okay.
Yes, sir.
Yes. I don't have any question, but I enjoyed listening this talk. I heard already about networking, and it is a very, very important new fields. Okay. It is a very informative and very good fields.
Thank you, sir.
Yes.
Thank you. Any question?
Thank you. I think so too.
So, Promise, you talked about node, but
yes.
You also showed the example of the bird flocking.
Mm-hmm.
How do you,
yeah.
Make
so
peace
when I talked about
with
bird
both?
flocks, I did not really have a network in mind, but that was just to illustrate what a complex system is and what how people define complex systems. I don't know how you could map a flock of birds into a network. Maybe there is
what I mean really was I mean, bird flock is also a chaotic square. So
I mean, in some sense, there is a network in.
Take account of what is it called?
So
chaos.
Yeah. Of course, yes, absolutely. But I mean, that's a whole area of research in active matter.
Yeah.
But if you're specifically looking for a network connection with these bird flocks, I could imagine you can have these geometric graphs that could represent this flock where, so what happens is that the bird can only see in its immediate neighborhood. So if you start with every bird as a node, and then you say that, okay, I'm going to have a connection if the distance between two birds is less than a certain number. And then you can draw these connections. And of course, this, okay, I'm making these things up as I'm talking. So, and of course, this network is not a static network because birds are moving. So it's a dynamic network where the structure of the network itself is evolving. But I don't.
Trying to think more, less of the words, more of the way we think, like how the neurons actually work together for us to be able to make sense of what we think and listen. So I know that certain part of the brains, when the neurons and the signals, they actually, I mean, the neurons are basically networks, right? I mean, and then nobody really knows how the end result is in the understanding that we actually develop, right?
Yes, exactly.
You're listening in that short of a time. We are able to process the information that I sent. I'm telling and to make sense, and then again think on that. So I don't know how effectively these things happen. It just boggles my mind that this happens so efficiently.
Yeah. So there are models that describe these bird flocks, but I don't know if they specifically incorporate any networks. But in the case of a neuronal activity and those kinds of network in the brain, there is an entire field dedicated to just inferring these connections between neurons. So you know the activity patterns, but you don't know which neurons are coupled or act together with which other neurons, and that's a great question.
Thank you,
Dr. Pramesh Singh. And Dr. Pramesh Singh explained how to use network models to study complex systems in detail. And he explained social systems and how the mathematical analysis of the model reveals the existence of a critical point in terms of a model parameter. And he explained the simulation on finite networks and social valence. Now, this talk was very informative and flavor talk. And thank you very much, Dr. Pramesh Singh, sir, for your talk. Thank you. Now, our next speaker is Dr. H.N. Pandey, and his talk is on the Ray-Chaudhuri equations. And I would like to introduce Dr. Pandey. Dr. Hemati Nandan Pandey is currently working as assistant professor in the Department of Physics, Gurukul Kangli University, Haridwar, and he is having charming personality. He has done his PhD from Kuma University, Nainital. His research area is high energy physics and classical gravity. He has published so many research papers in national and international research journals, and he got so many awards, DAD fellowships, and Kothari fellowship by University Grant Commission, Silver Jubilee Awards from Kuma University, Nainital, and so on. He has been visited so many countries like USA, UK, and he is associated with so many academic and scientific bodies. And Dr. Pandey is a member of several research and academic bodies, and currently he is associated with the IUCA Pune, IMS Chennai, IIT. And now with these remarks, I would like to invite Dr. Hemati Nandan Pandey for his talk on the Ray-Chaudhuri equations. Pandey sir, you are welcome.
Hello, am I audible to you?
Yes, sir, you are audible.
Okay, so let me start with thanking to Bhupesh and others, Dr. Mahipal, Dr. Subhash, for this nice effort to organize this e-conference. I think the people here are mostly from the background of material science, so it's a little bit difficult job to do while speaking about the Ray-Chaudhuri equations. Could you see the screen over there? My presentation is
no.
Not yet, sir.
present now, and then your entire screen. Is this possible to see now? It's okay? No?
Sir, it is not visible, sir.
Okay, let me check it again. And if from beginning, is this now? Could you see this?
No, sir.
Then what's the problem then? Then what to do? Then I'm just
Click the button.
yes, and then a window. Right? Your entire screen, fine, but
And select that screen also.
okay, let me check it here. Share. Stop sharing. Is there? No? Not
Yes,
yet?
yes, yes.
You can see it now? You can
Yes,
see
sir.
my first slide?
Yes, sir. Yes, sir. Yes, sir.
Okay, okay. So, fine. Let me start with this title, the Raychaudhuri equations. And let me first tell you about my plan. I will be telling you first about this gentleman, Professor Amal Kumar Raychaudhuri, and his famous equation. Actually, this equation became quite famous when Stephen Hawking and Rosalind Penrose used his famous equation on expansion scalar in cosmology for the purpose to explain the singularity theorems in general relativity. And afterwards, these equations are being used in many areas in classical gravity and cosmology. I will let you know about examples of these equations in the background of flat and curved space-time. But particularly, I will quote these equations to study the geodesic flows around curved black hole, which is a rotating black hole space-time. And the purpose to take the curved black hole for this study is because all the black holes in our universe, as our observations tells us, are rotating ones. And then I will summarize few results, and there are certainly some open issues and good opportunities for young people those are working in mathematics and physics, especially in theoretical physics, to work on these equations. This is still an open area to do some work. So let me first tell you something about A.K. Raychaudhuri. Actually, you know, the equations, identities, and inequalities, they are really important in science, or in particular in mathematics and physics. And they, without these equations, identities, and inequalities, it's very difficult to understand certain phenomena. And some has ubiquitous influence, like the Laplace equation, you know. We use Laplace equation in various diverse situations in physics, in different branches of physics. And in my opinion, one more such example is Raychaudhuri equations, though initially it was derived in theoretical cosmology, but now we can certainly use in different branches of physics. I will let you know why we can use this in different branches of physics. And certainly this is one of the few equations those bears the name of its a discoverer. I mean, Raychaudhuri. You know, there are few discoveries those bears the name of their who discovered them, like you know Raman effect and ionization equation. In particularly in Indian context, if we see Chandrasekhar limit, post condensation, Vaidya space time, and one such equation is also Raychaudhuri equation. Basically, it's a geometrical statement. So once it's a geometrical statement, if you change the background geometry, you can apply this to diverse situations, depending on the geometry of particular space-time taken for our purpose. Historically, you can see over the screen that this equation looks like theta dot plus 1 3 theta square plus sigma square minus omega square plus r alpha beta u alpha u beta is equal to 0. Here you see few quantities like theta, this is expansion scalar, sigma is shear, omega is rotation, and this r alpha beta is this Ricci tensor, and u alpha u beta is 4 velocities. And this equation was actually historically, this looks like this, and this equation was used by Stephen Hawking and Roger Penrose for the derivation and explanation of the similarity theorems in general relativity. And not only this equation, but we have two more equations, one for the shear and one for rotation as well. And Professor Rai Chaudhary, actually born at a place, Barasil in Bangladesh, now in Bangladesh. At that time it was in India. And he died in 2005. You can see the details over there. It has a great contribution. But let first try how these equations actually evolve and what does it mean actually. I will try to correlate the situation with 3 examples. Let us consider first example, first scenario, a lecture room, not in a true sense, right? You can see there are 2 figures, A and B, and this good and bad, you can see. If the students are looking towards the speaker, towards a fixed point, I mean the vector field of look at directions of students' eyes. In first figure, the arrows actually focus towards a point on the screen. So some sort of focusing is there. And in the second, in the B, figure B, arrows are actually haphazardly distributed. So there is a defocusing kind of situation. This might be a situation in a classroom and in a lecture theater. Now, for time being, just remember this example. Now, let us think about another interesting example. Suppose you are given with a rubber disc or a deformable media, and you give some initial condition to this, then what do you expect? There could be 3 situations. First is that initially you had some area A1, and then later, after giving some initial conditions or to some stress to it, there could be expansion. I mean, the area has increased. And there could be a possibility that area remains same, but the shape of the disk has changed. Now it becomes elliptical. And in the third situation, that both area remains same and the shape also same, but there is a rotation. So essentially, there are 3 defining features of the disk when we talk about the deformation of this media, this deformation of this rubber disk. So one is expansion, the next one is shear, and third one is rotation. I will call these 3 parameters often as ESR variables. And let us think about a third example, third scenario, which is the case of flowing fluids, right? We know the fluid flow lines are actually, they represent some flow. And you can see in the figure that at some extent of this parameter lambda 1, the area enclosed on the left hand side, you can notice it, and later on the right hand side, you can notice the area is now bigger. So there is a positive expansion, right? Area at initial stage is less than at final stage. And you can also observe the twisting in the flow lines. So there is also more or less the same situation like what we have seen in our example number 2. So we need to have these 3 parameters again, expansion, shear, and rotation, to understand the kinematics of the flow of these fluids actually. In recent years, we have done some work in this, but let me first tell you about the message, what we learn, what we can learn, what one can learn from these examples. You see, in each case, there is a vector field which is evolving along a parameterized direction. In the first case, then the example of a lecture theater, the parameter, the look at direction could be spatial. And the second example, it could be time, the deformation in this rubber disc evolving with time. And the third example, it could be an arbitrary parameter, the flow of the fluid. So you can actually um, consider some arbitrary parameter to label the points of this fluid flow. And the equations, those actually govern the evolution of these three quantities, expansion, scalar, shear, and rotation, are basically the Raychaudhuri equations in a very, very generalized sense. I already told you this is a geometric statement, so their evolution will definitely depend on the background geometry. I will come to this very soon. But let me tell you about few references and work done by us. You can see we have done some work on deformable media, which is because it's written outside the realm of GR, general relativity. I mean, we have taken some flat space things and we have worked on that. Then later we have worked these equations in the background of curved surfaces, sphere, hyperbolic space. Even we have worked with the torus geometry, and onwards we have extended this work for geodesic flows in the black hole space times. Those arise in string theory, and again we have extended this works for Kerr black hole space time and other black hole backgrounds too. I will mainly focus on the Kerr black hole space time later on. You can see the details of the work in these papers by our group, our collaborators, and my research students. So now let us try to understand how the deformations actually evolve. How to quantify these deformations, right? In terms of these equations. Now you can see in the picture on the left hand side, suppose there are the particles on the surface or on this surface. At T1 instant, there are two particles, and if you give some initial condition to them, they will be at some position at T2, given with some blue arrow. And if you really think about some schematic view of this, what is going over there, you can think about on the right hand side, you can see the schematic view, this vector xj, and then it's the next particle is connected by some xi I t. And later on, when you have given some initial condition to it, then they moves on this position of xj and xj plus jj. You can see on the upper side xi I t plus delta t. And mathematically, you can easily write down the equation, whatever written in this equation over there. And then xi I dot means how this xi I, the deformation vector, is actually evolving with respect to this parameter. Maybe here you can think it's like a time. And on the right hand side, you can see the velocity gradient over there. And this velocity gradient is then written as Bij. And this Bij is known as deformation vector. Deformation, it encodes all the deformation things. All the deformation means it encodes all these kinematical quantities: expansion, scalar, shear, and rotation. For time being, if you just think about a two-dimensional space, then this Bij will be 2 by 2 matrix. And you know, a 2 by 2 matrix, you can just decompose it in 3 parts: trace free, and the trace part, trace free symmetric part, and then anti-symmetric part. So this trace part is actually plays the role of expansion scalar. The symmetric trace free part, it plays the role of shear, and the anti-symmetric this part, it plays the role of actually rotation. So that way you will have 3 quantities. And in order to do the kinematics of this, you can again differentiate this xi I dot and you can have a second order differential equation you can see over there. But if you think about the curved space time, you already know there is a geodesic deviation equation in GR. See the equation number second and this screen. And if you compare the first and second, then you have evolution equation of the velocity gradient or the deformation tensor Bij. You can see Bij dot plus these terms, right? So Bij actually encodes every information about this system. Okay. If you just think about a flat space-time, then the right-hand side, which actually includes the curvature part, this Ri, Lj, and this Riemannian piece over there, it will become actually 0. Fine. So for next slides, we will actually consider the velocity vector fields time-like throughout, as we are interested in the motion of real test particles in these space-time backgrounds, in the space-time background of a curved black hole. So we are considering this velocity vector field UL, UM, whatever, there as time-like. So if this is a time-like vector field, then it will have certain constant over it. But in 4D, for a congruence of time-like geodesics, you can actually write down your space-time piece into two parts, right? And it's transverse and longitudinal part. You can see the transverse metric H alpha beta can be written as the combination of G alpha beta and the U alpha U beta with this constant U alpha is -1. This is nothing but because of the time-like constant over there. And you can actually decompose your this evolution tensor in three parts. You can see the first part 1/3 theta H alpha beta. This is your trace part. This sigma alpha beta, you can just see this is symmetric and trace-free part. And last one, this omega alpha beta, is antisymmetric part. So this equation with this definition of this decomposition of the B alpha beta, which encodes theta, sigma alpha beta, omega alpha beta, and the equation for B alpha beta dot, the first order differential equation for the evolution of B alpha beta, it actually gives the three equations which you can see over there. First equation here is for the expansion scalar. Second equation here is for the shear, and third one is actually for the rotation. And you can see they are the first order differential equations. They are coupled to each other. They are nonlinear as well as inhomogeneous. And this set of equation is actually true for any four-dimensional space-time background. Only thing, the things will get changed when you fix geometry. Whenever you will fix the geometry, and you can actually find the true meaning of these geometric parts over there. This, like in first equation, R alpha beta, U alpha U beta, this Raychaudhuri scalar, you can just calculate this by using the Einstein equations in GR. Even if not, if you have the space-time given to you, you can easily calculate that. And then you can try to solve these equations to understand the kinematics of geodesic flows and evolution in a given space-time background. So for the time being, as I already mentioned you, that I will be trying to solve these equations for curved black hole space-time background, and the space-time geometry for the curved black hole space-time is given by this line element. You can see this, and you can immediately notice that in addition to the coordinates, there are two parameters, J and N. J is actually for the rotation, and M is the mass parameter. But their ratio A is actually curved spin parameter. And once this spin parameter is not there, this curved black hole space-time geometry goes back to the flat black hole space-time geometry. And this space-time geometry is Ricci flat. Actually, in this case, this R alpha beta is 0. So we say this Ricci tensor piece has gone, so it's Ricci flat. And by using this geometry, these equations now reduced in this form. You can see again, there are the three equations for these kinematical quantities, and you can immediately notice in the first equation this piece has gone, this R alpha beta, U alpha, U beta. But in the second part, there is still wild tensor sitting over there. And they are actually coupled equations. So whatever geometric influence is because of the Kerr black hole, the curvature is still there. And it is actually coming out through this wild tensor piece over there. C, in the second equation, you can notice C alpha, beta, and beta delta, this piece over there, right? And it's really very difficult to solve these equations analytically. Very difficult. It's very hard to do that. In some cases, and in flat space background, we have analytically solved these equations. But in four-dimensional setup, we are we don't have still any clue how to solve them analytically. I mean exact solutions. So in the absence of analytical solutions, what we do is that we try to solve these equations numerically by using some codes in softwares, right, like Mathematica and Mathematica, MATLAB, and then try to analyze what actually happens, how these kinematical quantities evolves, and what how they get changed with the parameters of the given space-time. So in this particular case, we have given a new definition to theta, and with this redefining of theta, we have a Riccati type of equation there. You can see f double dot plus hf is equal to 0, and we have written this b alpha beta, and we can construct it as an equatorial plane of freely falling frame, and the components of shear and omega you can notice over there. Then with these, and by solving these, we have noticed few interesting things over there, and I can actually mention to you that what these interesting points are. When this h is greater than 0, this piece sitting over there, h, you can see again this equation, f double dot plus hf. Many of you have seen this, right? This equation is quite popular. You can think about a harmonic oscillator kind of situation there. Then if h is greater than 0, then there are conjugate points exist, and focusing and defocusing can take place. But if h is equal to 0, there is no finite time singularity for initially non-contracting convergences. Fine. And these are really technical ones. If you have not gone through GR steps, it might be a bit difficult, but still I will try to explain this. But one interesting thing what we have actually learned from our analysis is that even if the change is initial shear and rotation, there is change in the critical value of the initial expansion scalar. And the features of this focusing, defocusing remains qualitatively same for extreme and non-extreme Kerr cases. And you can actually visualize what I mean by focusing and defocusing. You can see this theta with this affine parameter lambda, there is a defocusing, right? You can see there's going, this theta is going, defocusing means this is going as plus infinity. You can see in this figures, and we have checked the role of initial rotation, and in one case we have taken no initial rotation, in other case we have taken some initial rotation. You can just notice omega 0 is equal to 0.1. So the escape of matter and energy from the black hole neighborhood, you can understand in that way what I mean by the defocusing, right? And the effect of the spin parameter A and initial rotation on defocusing is clearly noticeable in these plots. And again in these plots, both initial rotation and A, you can see is actually going to advance the time to singularity, I mean defocusing here. And in the next plot, I will show you The focusing of theta, I mean, when theta is going to minus infinity with a fine parameter, and focusing with some critical initial expansion scalar is clearly shown over there. And one interesting thing one can notice that initial rotation delays the focusing, while with A, the spin, the curve spin parameter, it has certainly opposite trend. You can notice it if you have, if you understand this, what I'm saying, right? And let me try to summarize the results and the future possibilities in the direction. The angular momentum parameter A, this J by M, it actually assists both the focusing and defocusing in curved black hole case. Larger the spin, earlier the focusing or defocusing. In contrast with the role of A, an increase in the initial rotation always assists defocusing and it delays the focusing in both the cases. So a very general result for applicable to any situation, any space-time background, we believe that the rotation always defies the convergence and shear always try to assist it, right? And the future possibilities, one can possibly study the accretion of matter into a rotating black hole space-time by using these equations. We are now in this, and we are trying to do some investigations that is this possible to study the accretion of matter into a rotating black hole, which is a very hot topic of research these days, by using the Raychaudhuri equations. And next is that we can also try to understand the kinematics of null geodesic flows. I mean, the photon, the motion of photons in these space, in the background of these space black hole space times. In this case, we have taken the time-like geodesic time. We have taken the real test particles, but we can also certainly study the null geodesic flows by using these beautiful equations. This is all what I was supposed to say in this talk, and I hope you could have understood few things, few new definitions, and I think I should stop now, and if there are any questions, I welcome you all. Thank you very much.
Any question? Any question? Nimai sir, any comment on the talk?
No comment. Very good talk. Very good. Very clear talk.
Thank you, sir. Thank you very much. Thanks a lot.
Thank you, Hemanti Nandan Pandey sir, for your beautiful talk. And you have explained the importance of Raychaudhuri equations in diverse contests.
Yeah.
And its mathematical treatment.
Yeah.
And what are the future possibilities of these Raychaudhuri equations?
Okay.
You have explained very well.
Yeah.
Thank you very much, sir, for your beautiful.
Okay. Thanks for
Thank you,
your
sir.
invitation.
Thank you.
Thank you. Thanks to all of you.
Thank you, sir. Now it is the time for lunch break. At 2:30 p.m. we will start next session at 2:30 p.m. sharp. Thank you and enjoy your lunch at your home. Stay home. Stay safe. Thank you. Thank you.
One more information, please, for the participants. Please join your respective group, which are allotted to for their presentation. Don't join other groups, otherwise you will not be allowed to present your paper in other groups. So you should keep in your mind that you should join in a right group at right time. So we will start the next oral presentation session at 2:30 p.m. Thanks a lot to all of you. Thank you, Nimai sir. Especially you are here this morning and continuously you are supporting us. Thanks a lot for that.
Yes.
Sir,
Thank you very much.
Sir, you should also present at early in the morning tomorrow at 10 a.m. You are invited for
Yes,
that.
yes, I will try. I will try. I will try.
Okay.
Okay. Thank
you,
you.
sir.
Thank you.
Okay, thank you very much.
Oh, Prameshji, thanks a lot.
Oh, I thank you.
I'm sorry, we could not provide you the sufficient time because we were running late.
Oh no, I think I took more time. At some point I lost track of time, so I had to finish it rather quickly. But that's okay. I have fun.
We will arrange a detailed lecture of you, means for college students. So, Rameshji.
Sure, why not?
Okay. Thanks a lot, sir.
Okay, thank you. Bye.
Thanks for everybody.